There's a ghostly smudge in our night sky, so faint it once seemed like a flaw in human vision. Yet it's an entire galaxy, 1 trillion stars deep, hurtling toward us through the dark. When Andromeda finally meets the Milky Way, what secrets will it reveal about how galaxies are born, evolve and collide? And could we ever get close enough to explore it before the impact rewrites our sky? Somewhere beyond our familiar constellations, a vast spiral turns, quietly rearranging the future of our sky. Its light arrives with the patience of deep time, carrying clues that refuse to stay buried. To understand Andromeda, we have to abandon the comfort of now and accept a stranger rule. Distance is also a kind of time. Every observation becomes a negotiation with limits, the speed of light, the reach of our instruments, and the fragility of human intuition. We will follow the thin chain of evidence that transformed a doubtful blur into a measured realm of stars, and then into a laboratory for how galaxies live. Along the way, we will read its disk and bulge like anatomy, where dust hides the youngest fires and starlight reveals the oldest bones. We will listen for the faint signatures of past encounters, streams, shells, and subtle distortions, etched into the outskirts like scars, and we will confront the invisible architecture holding it all together, an unseen mass that shapes orbits, governs growth, and resists easy explanation. This is not only a story of what Andromeda is, but of what it remembers and what it is becoming. Because in the local group, gravity writes long sentences, and the ending is already in motion even if it arrives slowly. The central question guiding our journey is simple to ask and difficult to face. What can Andromeda teach us about the making of galaxies and about our chances of ever reaching one? We will move from naked eye wonder to precision measurement, from ancient starlight to future trajectories, without outrunning the evidence. And when the numbers turn personal, when distances become travel times, and discovery becomes commitment, we will test what exploration means on an intergalactic scale. What emerges is a portrait of a neighbour that is not merely distant but instructive, mysterious, occasionally violent, and with enough patience, knowable. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now settle in for a journey. First we return to the moment the universe grew larger than anyone imagined. Then we cross the dark where light itself becomes a timestamp. From there we dissect Andromeda's structure, uncover its hidden history, trace its approaching choreography, and ask what it would take to go. In a truly dark sky, a faint smear hangs where no star should be. It looks like breath on glass, or a flaw in the night, and your eyes keep returning to it. The longer you stare, the more it seems to gather itself, an oval hush of light suspended among sharp pinpoints. It does not twinkle like a star, and it does not drift like a cloud, and yet it stays, night after night, fixed among the constellations as Earth turns beneath it. This is Andromeda, catalogued as M31, visible without a telescope when the air is dry and the horizon is clean. In a rural sky it can feel almost accidental, as if the universe forgot to erase a brushstroke. In a city it vanishes completely, swallowed by sky glow, which makes its existence feel even stranger. It is immense, and it hides in plain sight. We begin with that contradiction because it defines the story we are telling. A tiny patch to the eye becomes a vast realm in the mind, and the mind resists the scale at first. The question is not only what Andromeda is, but what it did to us. It forced a change in scale so violent that the universe effectively doubled, then multiplied, then refused to stop expanding. It turned the Milky Way from everything into one example, one member of a much larger family. This documentary follows a method as much as an object, because the method is what made the object real. We will travel outward in distance and backward in time, using light as both messenger and archive. We will treat Andromeda as a mirror for our own galaxy's past and future, because it shares our basic spiral architecture. We will ask what secrets it holds about how galaxies form, evolve, and collide, and why their histories are written in faint structures. We will also ask whether humans could ever get close enough to explore it, even in principle, given what a light year actually means. For most of human history, Andromeda was a naked-eye mystery with no agreed meaning. Ancient observers noticed it as a persistent blur, distinct from the sharp points of stars and they returned to it like a familiar landmark. Some cultures folded it into myth, others into practical sky lore, but the object remained, quietly indifferent to interpretation. Medieval astronomers recorded it as a small cloud in the northern sky, a steady patch that did not behave like weather. It entered lists and star atlases as a fixed, unresolved light, drawn with soft edges because no one could draw it any other way. That word unresolved mattered, because it shaped the early category of nebulae. Nebulae were not yet clouds of gas or distant galaxies, or anything specific in a physical sense. They were simply fuzzy things that refused to become stars, even when you stared until your eyes watered. In that ambiguity, Andromeda sat like a test of perception, an object that challenged the boundary between what the sky contained and what the human eye could separate. Was it a nearby luminous cloud, a cluster of countless stars, or a trick of optics and fatigue? Even the language carried uncertainty, because astronomy was still learning how to name what it saw. A nebula could mean a true cloud, a dense star swarm, or something entirely unknown, and the categories overlapped. The sky offered appearances, not labels, and appearances can mislead. When you cannot resolve an object, you cannot count its parts, and without parts you cannot easily infer distance. The smudge stayed stubbornly whole. Then the telescope arrived, and the mystery sharpened without breaking. Early instruments pulled more light from the smudge, stretching it into an oval glow that looked less like a stain and more like a structured object. Observers saw hints of a brighter core, a gradual fade outward, and subtle asymmetries that suggested depth. In good conditions, dark streaks seemed to cut across the light, like shadows laid over something luminous. But the view did not resolve into individual stars, and that absence kept the debate alive. Andromeda stayed a nebula, possibly inside the Milky Way, possibly not, because the telescope revealed form without revealing scale. A nearby cloud and a distant star system can both look like a soft patch if your instrument cannot separate points of light. The problem was not curiosity, it was physics. Light spreads out with distance, and the farther an object is, the more its details collapse into a blur. The telescope improved the image, but it also made the question sharper. If this had structure, what kind of structure was it? As telescopes improved, astronomy gained confidence and also new confusion, because better data exposed deeper uncertainty. The Milky Way itself became a system to map, with stars distributed in patterns that hinted at a flattened disk. Star counts suggested density changes, and the band of the Milky Way across the sky looked like a clue to our own shape. But dust and gas complicated every line of sight, dimming distant objects and faking boundaries that were not real. A region could look empty simply because starlight was being absorbed. The question of scale became a trap, because the galaxy's size was uncertain and the sun's location within it was still debated. If the Milky Way was enormous, then Andromeda could be a small internal cloud projected against the outer reaches. If the Milky Way was modest, then Andromeda might be something else entirely, an external system seen from afar. Either way, the same smudge sat in the same place, refusing to confess its distance. By the early 20th century, two competing pictures of the universe faced each other, and both were plausible within the limits of measurement. One model treated the Milky Way as essentially the whole cosmos, with nebulae as local objects scattered inside it. The other model proposed island universes, separate star systems scattered through space, each one a galaxy in its own right. Both sides had data, and both had gaps that could not be closed yet because the crucial yardstick was missing. The argument was not philosophical, it was technical, and it demanded a distant scale that could reach far beyond the solar system. Parallax, the tiny shift of a star against background stars as Earth moves, worked only for nearby objects. Beyond a certain point, the shift became too small to measure with the instruments of the time. To decide what Andromeda was, astronomers had to build a ladder of methods, each rung calibrated by the one below. In 1920, that tension crystallized in the Shapley-Curtis debate, a public confrontation between two ways of sizing the universe. Harlow Shapley argued for a very large Milky Way that contained the spiral nebulae, and his case leaned on globular clusters. These dense spheres of old stars orbit the galaxy, and their distribution pointed to a center far from the Sun. Shapley used them to relocate humanity from the middle of the Milky Way to a more ordinary suburb. In Shapley's picture, the Milky Way was big enough to swallow the mystery. If our galaxy extended far beyond what earlier maps suggested, then the spirals could be nearby objects within it. He saw the spirals as local, perhaps forming stars, perhaps forming planets, but still inside our system. His universe was radical in one way, decentering the sun, while remaining conservative in another, keeping the cosmos largely contained. Heber Curtis argued for a smaller Milky Way and for the spirals as separate galaxies, and he assembled clues that pointed outward. He pointed to novae seen in spiral nebulae that seemed too faint to be local, implying great distances. He noted the dark lanes and spiral structure that looked like a self-contained system, not a wisp of material. He emphasized that the spirals were too numerous and too widely spread to be mere internal clouds, because their distribution across the sky did not match a disk-bound population. Curtis made the universe big enough to contain many Milky Ways, and that move carried a psychological weight. If the spirals were galaxies, then the Milky Way was not the stage for everything, but one stage among countless others. The debate did not end with a clear winner, because the key measurement was missing, and the evidence could be interpreted through either lens. Everyone needed a reliable way to measure distances far beyond parallax. They needed a standard candle, an object whose true brightness could be known with confidence. If you know how bright something really is, you can compare it to how bright it looks from Earth. That comparison turns light into distance because brightness falls off predictably as you move away. The logic is simple, but the calibration is unforgiving, and small errors become huge at cosmic scales. The breakthrough came from a quieter place than the debate stage, in careful work that did not look like revolution at first. Henrietta Leavitt studied variable stars in the Magellanic Clouds, using photographic plates that captured the sky as a kind of time-lapse archive. She noticed that certain variables, Cepheids, pulsed with a regular rhythm, brightening and dimming like a steady heartbeat. More importantly, she found a rule linking period and luminosity, hidden in the pattern of their changes. The longer the pulse cycle, the brighter the star truly is, and that relationship is rooted in stellar physics. A Cepheid expands and contracts because its outer layers trap and release heat in a repeating cycle, changing opacity as it does. When the star swells, it cools and dims, then it compresses, heats, and brightens again. The period depends on the star's size and internal structure, which also ties to its intrinsic luminosity. That relation turned Cepheids into distance markers, not because they were exotic, but because they were reliable. You measure how fast the star brightens and dims, and you infer its intrinsic brightness from Leavitt's relation. Then you measure how bright it appears from Earth, which is what your telescope actually records. The difference between intrinsic and apparent brightness reveals how far away it must be, because distance dilutes light. It is a simple logic built on careful calibration, and calibration is where astronomy either stands or collapses. Cepheids in the Magellanic Clouds were assumed to be at roughly the same distance from us, so their relative brightness could be compared meaningfully. Later, nearby Cepheids with known distances would anchor the scale more firmly, tightening the ruler. The universe had offered a measuring stick, and astronomy had to learn how to hold it straight. Leavitt's discovery did not instantly solve Andromeda, because it still required powerful telescopes and patient observing. Cepheids in other galaxies are faint, and they hide among crowded star fields where many points of light overlap. You need sharp images, repeated exposures, and the discipline to track tiny changes over weeks. You also need to avoid being fooled by other kinds of variables, or by photographic artifacts that mimic variability. Edwin Hubble entered that moment with access to the 100-inch Hooker telescope at Mount Wilson, one of the world's most powerful eyes. He targeted the Andromeda Nebula, photographing it over time, because time was the key. He looked for points of light that changed, since variability could signal a Cepheid with a measurable period. In 1923 and 1924, he identified such stars within Andromeda's glow, marking them on plates like a detective circling evidence. The steps that followed were methodical, not dramatic, but the conclusion was explosive. Hubble measured the period of each Cepheid, reading its true luminosity from Leavitt's relation, and he did it star by star. He measured the apparent brightness on the photographic plates, accounting for the limitations of emulsion and exposure. He compared the two values and computed the distance, translating faintness into remoteness. The numbers placed Andromeda far beyond the Milky Way, at a distance so large it could not be explained away. Even if earlier estimates would later be refined, the qualitative result was unmistakable. Andromeda was not a nearby cloud, and it was not a minor feature of our galaxy. It was a separate galaxy, an island universe of stars, and the word nebula suddenly felt like an old mistake. That single result broke the old universe open, because it forced a redefinition of what the sky contained. The Milky Way became one galaxy among many, not the container of all things, and the change was not gradual. Overnight, the scale of the cosmos expanded beyond familiar imagination, and the night sky became a facade for depth. What looked like a dome became a layered wilderness. The immediate consequence was not just a larger map, but a new set of building blocks for cosmology. Galaxies became the fundamental units of cosmic structure, and the universe became a population rather than a single city. Nebulae were reclassified, and the sky's fuzzy patches gained identities and distances, turning catalogue entries into physical places. With that shift came a new question about origins and evolution, because a population invites comparison. If there were many galaxies, then they could be sorted, measured, and understood as a class of objects. Why did some have spirals and others not? Why did some shine with active star formation while others looked quiet and old? What did environment and gravity do over billions of years? Andromeda, once a smudge, became a nearby laboratory for these questions. Andromeda sits about 2.5 million light-years away, close enough to study in detail, far enough to humble us. A light-year is not a time unit in this context, but a distance, how far light travels in a year. That means the photons reaching your eye tonight began their journey when early humans were shaping stone tools. The smudge is not only far away, it is also long ago. It is a spiral galaxy, larger or comparable to the Milky Way by some measures, with a bright central bulge and a wide disk. In long exposure images, its arms show lanes of dust and knots of blue-white stars, which signal recent star formation. The galaxy's light is not uniform, because its stellar populations vary with location and age. Even from afar, the structure hints at dynamics: stars orbiting, gas compressing, and patterns persisting. It contains hundreds of billions of stars arranged in a disk, a bulge, and extended arms, and its mass is dominated by what we cannot see. Around that bright disk lies a vast halo, thin but enormous, filled with older stars and dark matter that outweighs the luminous parts. Dark matter does not emit light, but its gravity shapes rotation and holds the system together. Without it, the outer parts of the galaxy would not orbit as they do. Andromeda has a system of satellite galaxies, smaller companions bound in its gravity, moving like moths around a lantern. Some are dwarf spheroidals, faint and diffuse, and others show signs of gas and star formation. Streams of stars arc through its outskirts, evidence of past mergers, as if the galaxy is wearing the torn ribbons of what it consumed. Even in outline, it is not static. It is a record of collisions and growth. It is also moving, and its motion points toward our future, which makes the story feel less like distant history. Because Andromeda is approaching the Milky Way, it is not only a distant object, it is a clock, counting down to a collision billions of years from now, governed by gravity's slow insistence. The approach is measured through tiny shifts in spectral lines, where motion leaves a fingerprint in light. That future encounter will reshape both galaxies, mixing stars and dark halos, and likely triggering waves of star formation as gas clouds compress. Individual stars will mostly pass by each other without direct collisions, because the distances between stars are vast. But the galaxy's overall structures will not survive unchanged, because gravity will rearrange orbits on a grand scale. The night sky of whatever beings exist then will be transformed beyond recognition. It will test our theories of how galaxies interact and transform, because mergers are a central engine of cosmic evolution. It will also force us to imagine what it means to belong to a galaxy at all, when a galaxy is not a rigid object. A galaxy is a pattern of motion, a gravitational ecosystem, and its borders are not walls. When two such systems overlap, what counts as home? So this chapter begins with a smudge and ends with a universe of galaxies, and the emotional arc is tied to measurement. The Andromeda Nebula becomes Andromeda the Galaxy, and the sky becomes deeper than it looks. The investigative tone comes from that transformation, because every answer changes the scale of the next question. When distance grows, time grows with it, and the past becomes visible in layers. Now, we cross the threshold that Hubble opened. We stop treating the smudge as a flat patch on the sky, and we let it become a three-dimensional realm with structure, history, and motion. The camera drifts closer, and the faint oval brightens into a crowded field of suns, each one a point of physics and time. We fall into its light, and the journey becomes physical, as if the night itself has depth. In the next chapter, we enter Andromeda's anatomy and we start reading the evidence written in its stars. We will follow the glow inward toward the bulge, outward along the arms, and beyond into the halo's faint outskirts. We will treat every lane of dust as a clue and every stream of stars as a memory. The smudge will stop being a smudge and it will become a place. Andromeda looks like a small smudge, but it is a delayed message carried intact across a gulf we cannot feel. Every photon arriving tonight carries a departure date, and the sky becomes a layered archive where distance and time are braided together. Even before we name it, light is already telling us when it left, because the universe enforces a strict speed limit. On a clear night, the galaxy's glow seems almost accidental, an oval haze hovering near familiar constellations. The patch is easy to miss, and that fragility is part of the lesson, because the signal is real yet barely above the background. Yet that faint blur is a whole stellar city, and its light arrives with a timestamp written by physics rather than by memory. The light from Andromeda left about 2.5 million years ago, and it has been travelling ever since without pause. On Earth, early hominins walked and hunted under changing climates, and stone tools were becoming more refined in a world that did not know astronomy. The landscape they knew was shaped by ice ages and shifting grasslands, while the photons we collect now were already crossing intergalactic space. Those ancestors never saw Andromeda as a galaxy, because even the concept did not exist. They saw a sky of points and patterns, while the photons that reach us now were already in flight. The human story moved forward in generations, but the light story moved forward in meters, each second adding another 300,000 kilometers. This is look-back time, the built-in delay of observation that no telescope can remove. We never see the universe as it is now, only as it was when light began travelling. The delay applies to everything: planets, stars, galaxies. So the night sky is not a snapshot, but a museum of different ages. Even the word now becomes slippery when the signal needs time to cross space. The present is local, and the farther we look, the more the universe turns into a record. When we say now about Andromeda, we are really naming a moment long gone, preserved only because light can coast through darkness. That delay is not a metaphor, it is geometry made visible. Space separates events, and light speed turns separation into time, so distance becomes a kind of history. Relativity makes this unavoidable, because information cannot outrun light, and causality depends on that limit. Light moves at a finite speed, about 300,000 kilometers per second, and that limit is woven into every image. A telescope is not a window that opens instantly, it is a receiver tuned to old broadcasts. Each exposure is a collection of arrivals, and each arrival is proof that the path was uninterrupted. When we point a camera at Andromeda, we are not catching it as it is. We are sampling a particular slice of its past, and that slice is defined by the path each photon managed to survive. The slice is also selective, because dust, gas, and instrument sensitivity decide which wavelengths reach our detectors. The central question sharpens here, because the past is not merely aesthetic. What secrets does Andromeda hold about formation and collision, if every measurement is already a glimpse of its earlier state? If we want to understand what it is becoming, we must first understand what it was when this light began its journey. Andromeda is also unique in human experience, and that uniqueness can mislead us. It is the only major galaxy most people can see without a telescope, and that fact hides a trap. Visibility feels like intimacy, and the sky encourages us to mistake detection for nearness. Naked eye visibility suggests closeness and simplicity, as if Andromeda is just another bright object. In reality, it signals a rare combination of true size, relative proximity, and a dark enough sky. Its total light is substantial, but it is diluted across a wide area, so the eye struggles to gather it. Under city lights, the smudge often disappears completely, and that absence is instructive. It tells us that Andromeda's light is not intense, but spread thinly across a wide patch of sky. The background glow rises, contrast collapses, and the galaxy's faint outskirts dissolve into the haze. When it does appear, it seems modest, almost shy, as if it is barely there. That impression is a failure of our senses rather than a measure of the galaxy's scale. The eye is not a long exposure instrument, and it cannot stack minutes of photons into one persistent image. We feel the gulf only when we translate it into scales the body understands. A light year is a distance, but it behaves like time in the mind. It forces us to think in travel and waiting, because nothing in daily life prepares us for millions of years of uninterrupted motion. A light year is the distance light travels in 1 year, roughly 9.46 trillion kilometers. The number is too large to picture, so the brain converts it into duration, and duration becomes emotion. Once distance becomes time, the cosmos stops being over there and becomes long ago. Start near home and compress the map as if the solar system were a model laid out on a long night road. The Earth-to-Moon gap becomes a few steps, a familiar pause between worlds. In that reduced world, the Moon is close enough to feel like a neighbour, even though it is still far beyond any ordinary journey. In that model, Earth is a small bead, and the Moon is a smaller one, separated by a span you could cross without thinking. The real distance is 384,000 kilometres, but the scale makes it intimate. You can almost imagine the Apollo trajectories as simple arcs, even though they demanded precise timing and velocity. Keep shrinking and the solar system becomes a neighbourhood that still feels roomy. The planets fit into a small model, yet the emptiness between them dominates the volume. The Sun becomes a bright point with a wide personal space, and the orbits become more like lanes than circles. Mercury and Venus become quick markers along the route, while Mars sits farther out like a quiet outpost. Even at this scale, most of the model is not objects but intervals. Those intervals matter because gravity acts across them, and sunlight thins across them, changing temperature and chemistry. Jupiter is suddenly a major landmark, and Saturn's rings become a thin suggestion rather than a spectacle. Uranus and Neptune drift toward the edge, and the Sun's warmth becomes an idea rather than a sensation. The heliosphere, inflated by the solar wind, becomes a bubble whose boundary is defined by pressure rather than by a visible wall. Push outward, and the Kuiper belt becomes a thin ring at the edge of that model. Beyond it, the Sun's influence continues in a fading gradient. The sunlight is weak, but gravity still governs, and the outer solar system keeps records in the slow choreography of small bodies. The Kuiper belt is not a wall, but a region, populated by icy bodies and dwarf planets. Its members are faint and cold, and their orbits preserve clues about how the solar system settled. Resonances with Neptune, like invisible grooves, shepherd many objects into patterns that hint at ancient migration. Then comes the Oort cloud, a spherical reservoir of icy bodies that may extend a significant fraction of the way to the next stars. In a scaled walk, it is the first place where the Sun feels far away. Here the Sun's gravity is still present, but it is so gentle that the galaxy itself begins to compete. The Oort cloud is inferred rather than photographed, assembled from the behaviour of long-period comets. Those comets arrive like messengers from deep time, nudged inward by passing stars and galactic tides. Their orbits are elongated and delicate, and their arrival direction suggests a distant, roughly spherical source. At that boundary, gravity becomes delicate, and the Sun's hold is easily disturbed. A slow encounter with a star even far away can reshape the orbits of distant debris. The perturbation is small, but over millions of years small changes accumulate, and the outer reservoir is continually stirred. After the Oort cloud, nothing changes for a long time, and the silence becomes the story. Interstellar space is not a new object. It is a long absence punctuated by rare stars. The nearest destinations are still so far that even our best probes would need tens of thousands of years to arrive. In that emptiness, atoms are sparse, and collisions are rare, yet physics still operates with patient consistency. Magnetic fields thread through the void, and cosmic rays pass like invisible rain. Even the vacuum has structure, because plasma responds to fields, and fields carry energy across vast distances. Even the nearest stars sit at distances that break intuition. On the same scale, the next star is not across town, it is across continents. The space between stars is not a gap in a neighbourhood, but a separation between islands in a dark ocean. Proxima Centauri is about 4.24 light-years away, and even that nearby distance is enormous in human terms. If the Sun were a grain of sand, the next grain would still be far down the beach. The metaphor works because the emptiness is the dominant feature, and the stars are exceptions. Now extend that emptiness to Andromeda, and the mind begins to resist. The 2.5 million light-year gap is not one leap, It is millions of years of uninterrupted travel. The distance is so large that even the Milky Way's disk becomes a small region inside a much larger separation. Imagine a photon leaving a star in Andromeda's disk while Earth's continents were arranged differently. It crosses intergalactic space without rest, and it arrives to be absorbed by a detector for a fraction of a second. In that instant of absorption, the photon's long journey ends, and our measurement begins. Along the way, the photon passes through regions that are almost nothing, and then through regions that are slightly less than nothing. It threads between galaxies, through thin plasma, and past drifting clouds of gas. The odds of hitting a dust grain are low, yet the odds of passing through ionized hydrogen are high, because the universe is mostly hydrogen. The tension of the journey is the tension of measurement, because our conclusions depend on the length of that path. If distance equals time delay, then an error in distance becomes an error in cosmic history. The same error also changes inferred luminosity, because brightness and distance are coupled by simple geometry. A few percent may sound small, but it shifts timelines, masses and energies. It changes how bright we think stars truly are, and it changes how fast the universe seems to expand. When the numbers move, the stories built on them move too, and the shift can ripple from one galaxy to the entire cosmos. So how do we measure it at all? We build a distance ladder where each rung is calibrated by the one below, and each rung carries its own biases. The ladder is a practical compromise because no single method reaches from Earth to the edge of the observable universe with the same reliability. The ladder is not a single technique, but a chain of trust, and the chain is only as strong as its weakest link. Astronomers learned this slowly, through decades of revision, argument and improved instruments. Each generation inherits the previous calibrations, then tests them, and sometimes discovers that an old assumption was quietly bending the scale. Historically, the stakes were enormous, because distance decides what kind of object Andromeda is. In the early 20th century, the Great Debate asked whether spiral nebulae were inside the Milky Way or far beyond it. The argument was not only about one object, but about whether the universe contained many galaxies or only one. When Edwin Hubble identified Cepheid variables in Andromeda, the scale of the universe expanded overnight. The smudge became a separate galaxy, and the Milky Way lost its claim to being the whole cosmos. That moment also reshaped philosophy, because it placed humanity in one galaxy among countless others, with no privileged central position. The first rung is parallax, the most direct geometric method we have. Earth's orbit shifts our viewpoint, and nearby stars appear to move against a more distant background. The effect is the same depth Q our eyes use, but the baseline is 2 astronomical units rather than a few centimeters. Over 6 months, we observe a star from opposite sides of Earth's orbit, creating a baseline of about 2 astronomical units. The star's apparent shift is tiny, but it is a real angle in the sky. The shift is measured against background stars that are effectively fixed at that precision, so the geometry becomes a ruler drawn on the celestial sphere. Parallax is simple in principle and brutal in practice, because the angles are extremely small. Beyond a few thousand light years, they shrink below older instruments, and the measurement becomes dominated by noise. Atmospheric turbulence, detector imperfections, and subtle spacecraft motions can all masquerade as a false wobble. A parallax of 1 arcsecond corresponds to 1 parsec, about 3.26 light years, and most stars have far smaller parallaxes. Measuring fractions of a milliarcsecond demands stability, calibration, and careful statistics. It also demands patience, because the signal is a slow annual cycle, and the baseline is fixed by the rhythm of Earth's orbit. For larger distances, we need objects with known intrinsic brightness, because geometry alone runs out. If we know true luminosity, apparent brightness becomes a ruler through the inverse square law. The method is elegant, but it depends on knowing what the object really is, which means understanding stellar physics rather than merely cataloguing light. Brightness falls with the square of distance, which is simple to state and easy to misuse. A star that looks 4 times dimmer might be twice as far away, or it might be obscured, or it might simply be different. The sky is full of imposters, and the distance ladder is a constant effort to separate true standards from lookalikes. Cepheid variables are the classic standard candles, and their value comes from physics rather than convenience. Their pulsation period links to intrinsic luminosity through stellar structure, turning rhythm into distance. When we time the pulse, we are effectively weighing the star's internal balance between pressure and gravity. A Cepheid swells and contracts because its outer layers trap and release heat in a cycle, driven by changes in opacity. Helium in the atmosphere becomes partially ionized, and that ionization acts like a valve. The star's envelope becomes a heat engine, and the engine runs because the gas changes how transparent it is as it warms and cools. When the star compresses, it heats, the opacity rises, and radiation is trapped, pushing the layers outward. When it expands, it cools, the opacity drops, and energy escapes, letting gravity pull it back again. The cycle is stable enough to repeat, yet sensitive enough that it encodes the star's physical size and luminosity. The result is a repeating pulse, and the period is tied to the star's mass and radius. Longer periods correspond to more luminous Cepheids, so time itself becomes the calibration mark. The relationship is not arbitrary, because larger, brighter Cepheids take longer to expand and contract, like larger bells that ring more slowly. RR Lyrae stars extend the method for older populations, and they occupy a different evolutionary stage. They are fainter than Cepheids, but more common in globular clusters and galactic halos. Their presence is a sign of ancient stellar populations, which makes them especially useful for mapping the outskirts of galaxies. RR Lyrae variables are horizontal branch stars burning helium in their cores, and their luminosities cluster in a relatively narrow range. That consistency makes them useful for mapping older, metal-poor stellar systems. Their periods are shorter than Cepheids, and their light curves have distinctive shapes that help identify them in crowded fields. Then come secondary indicators that push farther, especially when individual stars blur together. The tip of the red giant branch marks a predictable luminosity cutoff for old stars. It works because low-mass stars reach a well-defined point before helium ignition, and that point is tied to core physics rather than to the details of the outer atmosphere. As low-mass stars exhaust hydrogen in their cores, they climb the red giant branch, growing larger and cooler. Just before helium ignition in the core, their brightness reaches a characteristic maximum in certain bands. The helium flash happens quickly in stellar terms, so the population piles up just below that peak, sharpening the feature we measure. That tip is sharp enough to act as a standard candle, especially in the near-infrared where dust effects are reduced. It is less sensitive to some stellar population differences, though not immune. The method is powerful in nearby galaxies like Andromeda, where we can resolve red giants across wide regions and compare different environments. Surface brightness fluctuations use statistics rather than individual stars, and they exploit a subtle fact about images. In unresolved galaxies, pixel-to-pixel variation reveals distance as the image smooths with remoteness. The technique turns the graininess of starlight into a measurable signal, which is useful when the galaxy is too far to separate stars cleanly. Nearby galaxies show more granular light, because fewer stars contribute to each pixel, so the variance is larger. Farther galaxies average over many stars per pixel, and the fluctuations diminish in a predictable way. In practice, the method demands careful modelling of stellar populations, because the typical brightness of the contributing stars affects the fluctuation amplitude. Each method sounds clean until calibration enters, and calibration is where astronomy becomes a craft. The latter works only if we understand what changes a star's light before it reaches us. The universe is not a laboratory bench, so we must infer corrections from the light itself, then test those in multiple, independent ways. Dust is the first complication, and it is everywhere, even when it seems absent. Interstellar grains absorb and scatter light, making objects dimmer and shifting their colours toward red. Dust is made of silicates, carbon-rich compounds and ices, and its distribution traces the same spiral structure that hosts star formation. Those grains are tiny, comparable in size to wavelengths of visible light, so they interact strongly with blue photons. Blue light is scattered and absorbed more efficiently, while red light passes more easily. The result is a colour shift that mimics age or temperature changes, which can mislead us unless we measure across multiple wavelengths. This is extinction and reddening, and it reshapes the information we receive. Dust can make a galaxy look farther than it is, because dimming mimics distance if uncorrected. It can also hide parts of a galaxy's structure, turning spiral arms into faint suggestions and erasing the lowest surface brightness features. Astronomers estimate dust effects by comparing colours across multiple filters, looking for the signature of reddening. They also map dust using infrared emission, because warmed grains glow at longer wavelengths. In Andromeda, dust lanes are visible as dark cuts in optical images, but their full extent becomes clearer when we add infrared data. Even then, dust is patchy, and its properties vary, which complicates correction. A line of sight through a spiral arm is not the same as a line of sight through a halo, and Andromeda has both. The correction is therefore probabilistic, built from maps, models, and the statistical behavior of many stars rather than from a single perfect measurement. Metallicity is the second complication, and it reaches into the star's atmosphere and interior. The abundance of elements heavier than helium changes stellar opacities, and it shifts the Cepheid period luminosity relation. In plain terms, a star with more heavy elements handles radiation differently, so its pulsation and brightness do not match a simpler universal curve. A Cepheid in a metal-rich environment can differ subtly from one in a metal-poor environment, even at the same period. If we ignore that, our standard candle is not standard. The effect can be small, but small is exactly what matters when we are trying to resolve a few % difference in cosmic expansion. Metallicity also affects stellar colours and temperatures, which feeds back into how we interpret brightness in different bands. The correction is not a single number, but a model that must be tested against data. That is why Andromeda is valuable, because it contains regions of different metallicity, letting us test how the relation behaves across environments. Crowding is another practical complication, especially in distant galaxies where stars overlap in a single pixel. If multiple stars blend together, a Cepheid can appear brighter, and the distance can be underestimated. The problem is worst in dense spiral arms and near galactic centers, where the background is bright and the star fields are thick. So distance work becomes a discipline of corrections, and the corrections must be justified. We measure colors, compare bands, model dust along the line of sight, and adjust for population differences. We also quantify uncertainty honestly, because a small hidden bias can climb the ladder and become a large cosmological error. We also cross-check methods against each other, because agreement is evidence that systematics are under control. Disagreement is not failure, but a clue that something is missing. When two methods disagree in the same galaxy, the galaxy becomes a diagnostic tool, revealing where our assumptions are too rigid. This is why Andromeda matters as a test case, and why it returns again and again in astronomy. It is close enough to resolve individual stars, yet far enough to stress the ladder's assumptions. It sits at a distance where multiple rungs overlap, so we can compare them directly rather than through a chain of intermediate galaxies. In Andromeda, we can find Cepheids in spiral arms, RR Lyrae in the halo, and red giants across the disk. The galaxy becomes a laboratory where multiple rungs overlap in the same object. That overlap is precious, because it lets us check whether dust corrections, metallicity corrections, and crowding corrections produce a consistent distance. Modern astronomy tightened the ladder with new tools, and the improvements are both technical and conceptual. The Hubble Space Telescope resolved Cepheids in crowded fields and reduced confusion from overlapping stars. It also provided stable, repeatable photometry, which is essential when we are measuring subtle brightness changes over time. Above the atmosphere, Hubble avoids the blurring of seeing, and its stable optics make photometry more reliable. That stability matters when the signal is small and the correction budget is large. In practical terms, it means we can trust that a measured change in brightness is astrophysical, not a ripple introduced by air or instrument drift. Hubble also allowed observations in filters that help separate dust effects from intrinsic color. With cleaner data, the period luminosity relation becomes sharper, and the scatter shrinks. When the scatter shrinks, the distance estimate becomes less sensitive to outliers and less vulnerable to one crowded field dominating the result. Gaia reshaped the foundation by measuring parallax for vast numbers of stars across the Milky Way. Better anchors mean better calibration for Cepheids, RR Lyrae, and the red giant branch. Gaia also reveals which calibration stars are binaries or have subtle motions, which matters because hidden companions can bias brightness and color. Gaia's precision turns parallax from a local trick into a statistical framework, where biases can be modeled and corrected. It also reveals subtle motions, binaries, and stellar populations that affect calibration samples. The result is a cleaner set of standard candles, tied more tightly to geometric distance, which is the most direct kind we have. As calibration improves, uncertainty bars shrink, and the shrinkage changes what we dare to claim. That is not cosmetic, because cosmology turns small percentage errors into different histories for the entire universe. A tighter ladder changes the inferred size of the observable universe, the age we assign to cosmic events, and the energy budget we infer from expansion. If we misjudge distances, we misjudge luminosities, and then we misjudge masses and energies. The universe does not change, but our inferred story does, and the difference can be profound. A galaxy that is slightly farther is also intrinsically brighter, and that brightness affects how we model star formation, supernova rates, and stellar evolution. A subtle thread runs underneath these improvements, and it refuses to go away. Different methods still disagree on the present expansion rate, and the H0 tension hints at missing physics or hidden systematics. The tension is a reminder that precision is not the same as truth, and that the last few percent are often the hardest. One set of measurements, tied to the local distance ladder, suggests a faster expansion today than the value inferred from the early universe. The discrepancy is small in absolute terms, yet stubborn in statistical significance. If it is not a measurement problem, it may be telling us that the universe changed its behaviour, or that our model is missing a component. In this chapter, the tension stays quiet but persistent, like a low note under the melody. If our ruler is slightly warped, then our story of cosmic evolution may be slightly wrong. The unsettling part is that both sides of the tension are built from careful work, which means the resolution may demand deeper understanding rather than a simple correction. Andromeda sits near the base of that story, close enough to measure carefully and important enough to matter. When we refine its distance, we're also refining the scale on which cosmology is written. It becomes a benchmark, not because it is exotic, but because it is accessible enough to be measured repeatedly with different tools. Distance also changes how Andromeda appears, and the contrast between appearance and reality is part of its power. Its disk spans several degrees on the sky, wider than the full moon by many times. The true outline is not obvious to the eye, because the outer disk fades gradually rather than ending at a crisp edge. If you could see surface brightness the way a camera does, Andromeda would be an enormous, ghostly structure. It would stretch across the sky like a pale cloud with a bright core and faint wings. The halo would extend even farther, a dim envelope that merges into the background like smoke thinning into night. Yet the eye sees only a small glow, and often only with averted vision. Andromeda has low surface brightness, so its light is spread thinly across a large area and fades into the background. The total number of photons may be large, but the photon density per patch of retina is low, and that is what perception cares about. This is an illusion produced by biology and atmosphere, and it is surprisingly strict. The galaxy is large in angular size, but our vision prioritizes contrast, not total photons. In low light, the retina shifts toward rods, and rods are excellent at detecting motion and edges, but poor at registering diffuse gradients. Airglow, thin haze, and scattered light add a luminous veil that competes with Andromeda's faint outskirts. The galaxy does not dim, but the background brightens, and the smudge retreats. Even a slight increase in sky brightness can erase the outer disk, leaving only the core as a small misleading marker. Telescopes and long exposures reveal what the eye cannot integrate, and the transformation feels like a reveal. The faint outer disk and halo emerge only when we collect light over time. The camera stacks arrivals, and in doing so it turns a whisper into a measurable profile pixel by pixel. In deep images, dust lanes carve dark rivers across the bright inner disk, and star-forming regions sparkle as blue knots. The contrast is striking, because the lanes are not empty. They are dense with cold gas and dust that block starlight. The blue knots mark young, massive stars whose ultraviolet radiation energizes surrounding gas, making nebulae glow. The halo extends farther than most people expect, populated by older stars and faint streams. Some streams are narrow and coherent, while others are broad and diffuse, suggesting different kinds of past encounters. The overall impression is that Andromeda is not a static island, but a system still settling from earlier mergers. Knowing the distance turns that apparent patch into a physical object, and the numbers become meaningful. Angular size becomes true size, brightness becomes luminosity, and structure becomes measurable. Once the scale is fixed, we can compare Andromeda to the Milky Way in a way that is more than metaphor. At roughly 2.5 million light-years, Andromeda's visible disk spans on the order of a couple 100,000 light-years, depending on how faint a contour we include. That makes it comparable to, and in some measures larger than, the Milky Way. The uncertainty in the disk's true edge is itself a clue, because it depends on how the halo blends into the background and how far the stellar populations extend. Distance also lets us translate motion into speed, and speed into gravitational mass. When we see stars orbiting, we can infer the mass required to hold them, including the mass we cannot see. The logic is old, the same logic that explains planets around the Sun, but the scale is vast and the missing mass is dominant. Andromeda is not alone in the dark, and its environment is part of its identity. It belongs to the local group, a small gravitational community embedded in a shared dark matter environment. The group is not a neat cluster, but a loose association, bound by gravity and shaped by a long history of mutual influence. The Milky Way and Andromeda dominate this group, and their mutual gravity shapes the motions of smaller members. Triangulum, M33, is smaller but significant, and dozens of dwarf galaxies orbit as satellites and remnants. Some of those dwarfs are likely captured, while others may be the surviving cores of systems that were partially torn apart. Some dwarfs are irregular and gas-rich, still forming stars in fits and starts. Others are faint spheroidals, stripped of gas and dimmed by time, their stars moving in loose ancient swarms. Their diversity is a clue to environment, because proximity to a large galaxy can remove gas through tidal forces and interactions with hot halo material. These galaxies share more than proximity, because they share a gravitational landscape. Their motions trace an invisible mass distribution, and dark matter provides the binding framework for the entire group. The visible stars are like lanterns hung on a much larger structure, and the structure is inferred from how the lanterns move. We infer dark matter because stars and gas move too fast to be held by visible mass alone. Rotation curves stay flat where they should decline, and satellite galaxies orbit as if embedded in a much larger halo. The same conclusion appears in different systems, which is why it persists, even though the dark component remains unseen. In the local group, dark matter is not just a concept, it is a map drawn in velocities. Each dwarf's trajectory is a test particle, and each stream is a record of tidal forces. When a small galaxy is stretched into a stream, the stream's shape and speed reveal the gravitational field that did the stretching. The local group is not isolated either, and its boundaries are porous in a larger structure. It sits within a wider network of galaxies and gas, shaped by gravity on scales far beyond any single disk. The group drifts within the cosmic web, and its future is tied to the slow pull of nearby structures. Between galaxies lies darkness that is not empty, and the phrase intergalactic space hides complexity. The intergalactic medium is a thin plasma, mostly hydrogen and helium, stretched across enormous volumes. It is ionized by ultraviolet radiation from stars and quasars, so it behaves like a dilute electrical fluid rather than a neutral gas. Its density is so low it defies intuition, sometimes only a few atoms per cubic meter in the emptiest regions. Yet over millions of light-years, that tenuous gas contains substantial mass and carries heat and metals. The mass is spread thin, but the volume is so large that the total becomes cosmically important. Those metals were forged in stars and carried outward by winds, supernovae, and galaxy interactions. Even the voids have been lightly seasoned by cosmic history, as if the universe cannot help but share its products. The enrichment is uneven, which means the intergalactic medium also preserves a record of where galaxies formed and how violently they evolved. The intergalactic medium gathers into filaments, and the filaments are not artistic metaphor. These filaments form the cosmic web, the large-scale structure that funnels matter into galaxies and clusters. The web is faint in direct images, but it appears in absorption signatures and in simulations that match what we observe. In simulations, the web emerges naturally from gravity, acting on tiny early density fluctuations. Over billions of years, matter flows along filaments toward nodes, where galaxies grow and clusters form. The process is slow and relentless, and it turns a nearly uniform early universe into a structured one without any guiding hand beyond physics. Galaxies grow by drawing from this web and by merging with neighbours, and the evidence is written in faint features. Even in the local group, faint streams and disrupted dwarfs show that growth is ongoing. The outskirts of galaxies are especially revealing, because tidal debris can survive there for a long time, like handwriting that has not yet been erased. Andromeda's halo contains stellar streams that arc like pale smoke, remnants of smaller galaxies pulled apart by tides. Each stream is a fossil record, and each fossil is a clue to how the galaxy assembled. The streams also tell us that Andromeda has had an active past, with mergers that may have reshaped its disk and triggered bursts of star formation. So the gulf between the Milky Way and Andromeda is not a clean void, even if it looks empty to the eye. It is a thinly populated medium with structure, motion, and a history of enrichment. The darkness is therefore not absence, but a low-density stage where gravity, radiation, and plasma continue their quiet work. When a photon crosses that gulf, it does not pass through nothing. It passes through a low-density environment shaped by gravity and radiation. The journey is quiet, but it is not featureless. Along the way, the photon may be slightly redshifted by cosmic expansion, and it may pass through hydrogen that leaves faint absorption fingerprints in other contexts. Distance measurement gives us coordinates inside that structure, and coordinates change the kind of questions we can ask. Once we know where Andromeda is, we can ask how it is built and what holds it together. We can place its streams in 3 dimensions, estimate their orbits, and connect their shapes to the mass distribution that guides them. We can compare its stellar populations to ours, and we can trace where its gas resides and where it has been lost. We can test whether its dark matter halo resembles the Milky Way's, or whether it carries a different history. Each comparison is a controlled experiment, because 2 large galaxies in the same group share some conditions, yet differ in details that matter. The act of looking becomes an act of time travel, and the phrase is literal rather than poetic. The Andromeda we study is not a present object, but a recorded state carried by light. The record is incomplete because it is filtered by dust and limited by sensitivity, yet it is still the best evidence we have. That fact does not weaken the journey, it defines it, and it disciplines our imagination. We investigate a galaxy by reading delayed signals, then reconstructing the dynamics that produced them. The reconstruction is careful, because it must respect both the data and the physics, and it must admit uncertainty where the data are thin. The reconstruction is a kind of controlled inference, where models meet measurements and are forced to agree. When they do not agree, we learn where our assumptions are too simple. Sometimes the lesson is technical, like an uncorrected bias, and sometimes it is deeper, like a missing ingredient in our cosmological model. Now we cross the threshold that Hubble opened, but with sharper tools and deeper stakes. The smudge becomes a timed transmission, and the dark becomes measurable. The same galaxy that once fueled debate now anchors calibration, reminding us that progress often begins with a single faint patch of light. We stand in a universe where even the nearest galaxy is far beyond touch, yet not beyond understanding. The question is not whether we can cross the dark, but what we become when we learn to measure it. When we accept the delay, we also accept a new kind of humility, because knowledge arrives only at light speed. Next, we move from distance to anatomy. With the ruler in hand, we can map Andromeda's parts, trace its mass, and test how galaxies endure. We move from distance to anatomy, because structure is history made visible. Andromeda is not a flat smear drifting in a black sky, and it is not a single object with one simple story. It is a layered system whose parts orbit, collide, and recycle. An ecosystem built from gravity, time, and gas. When we look closely, we are not merely admiring a shape. We are reading a record written in light and motion. Our first close pass skims the disk in a wide panoramic sweep, like a slow aerial glide over a luminous continent. Starlight brightens toward the center, then thins outward into a fading edge that dissolves into the background. The glow is not smooth, because countless unresolved stars blend into a granular haze, like sand seen from high altitude. Dust lanes cut across the light, not as empty gaps, but as cold material in silhouette. Those lanes create depth cues because they sit in front of brighter stellar fields and swallow their photons. In places, the lanes fork and braid, suggesting multiple layers of clouds stacked along our line of sight. Some segments look sharp and ink dark, while others fade into smoky translucence as the dust thins. The disk already feels like a stack of overlapping components, each one hiding the next. Even the disk's brightness has a physical meaning, because it roughly tracks where stars are concentrated and how they are distributed. The central regions glow warmly, dominated by older, redder stars that have had time to accumulate. Farther out, the light becomes more punctuated, where young clusters and star-forming complexes add blue-white highlights. The disk's edge is not a hard boundary, because stars and gas extend beyond what casual images show. The apparent end is often just where the surface brightness drops below a camera's sensitivity. The disk is a rotating sheet of stars, gas and dust, shaped by angular momentum conserved from its formation. Most of Andromeda's visible light comes from this flattened region, where billions of stars orbit in roughly the same plane. Yet the disk is not uniform because spiral structure organizes both matter and time. Where the disk is calm, stars age quietly and drift, their orbits slowly stirred by encounters and collective gravity. Where the disk is compressed, new stars ignite and mark the pattern, briefly outshining older populations. The disk is therefore both a map of where mass resides and a diary of where gas recently turned into light. If we could watch for a few 100 million years, the disk would look less like a painting and more like a fluid. Stars follow nearly circular paths, but gas behaves differently because it can collide and radiate away energy. That difference matters because it lets gas respond sharply to compression and shock rather than simply passing through. Differential rotation adds another twist, because inner regions orbit faster than outer ones and shear patterns apart. The result is a disk that is both stable and restless, held together by rotation, yet constantly reshaped by waves. Spiral arms look like fixed features, but they are better understood as moving traffic patterns. One idea is density wave theory, where arms are long-lived regions of higher density that rotate with their own pattern speed. Gas enters the wave, slows and compresses, then exits after forming stars. The arm persists as a pattern even as individual stars pass through it on their own orbits. In this view, the arm is not a rigid structure but a gravitational ripple that organizes orbits. It is a way for a disk to keep a coherent design while its contents continually change. Density waves also explain a subtle visual clue that telescopes often reveal. Dust lanes tend to sit on the inner edge of an arm, where gas first hits the compression. Bright blue star clusters appear slightly downstream, after collapse and ignition have had time to proceed. That offset is a kind of time arrow written into the disk. Shock first, then birth, then dispersal. It is also a reminder that what we see at one moment is a sequence stretched across space. Another idea treats arms as transient, repeatedly forming and dissolving through gravitational instabilities. In this view, arms are not permanent waves but short-lived structures that emerge where the disk becomes locally self-gravitating. They can be triggered by internal disk dynamics or by tidal nudges from companions that disturb the balance. Simulations show arms that shear, reconnect and reform, more like weather than architecture. The disk becomes a self-excited system, where gravity amplifies small irregularities into large patterns. If that is true, then each arm segment is a temporary solution to a constantly changing equation. Both pictures agree on the key mechanism that matters for star formation. Gas clouds respond to gravity and compression more strongly than stars do, because gas can cool and clump. When gas is squeezed in a spiral pattern, its density rises and cooling becomes efficient. Dense pockets collapse into clusters, and massive young stars appear quickly. The arms become a conveyor belt that turns diffuse gas into bright, short-lived beacons. The beacons are brief, but their influence is outsized because they reshape the surrounding medium. The physics of that collapse is simple in outline, even if messy in detail. Gravity pulls inward, while thermal pressure and turbulence resist, and the contest plays out across many scales. When cooling removes heat faster than compression adds it, pressure support weakens and collapse accelerates. The densest regions can fragment, producing multiple stars rather than one, and that fragmentation sets the initial architecture of clusters. Magnetic fields and feedback complicate the process, but they do not erase the basic fact. Dense, cold gas is the raw material of stars. A galaxy's spiral structure is therefore not just decoration, because it is a machine for concentrating that raw material. We confirm that story by changing the kind of light we collect, because different wavelengths reveal different temperatures and processes. In visible light, we see the combined glow of many stellar ages, weighted toward long-lived stars. In specific emission lines, we isolate ionized gas around newborn stars, separating it from the broader stellar background. In ultraviolet, we catch the hottest young populations before they drift away and fade. In infrared, We detect dust warmed by starlight, including light hidden from optical cameras. Multi-wavelength astronomy becomes dissection, because each band isolates a different physical process. It is like switching from surface photography to medical imaging, where each scan highlights a different tissue. H-alpha emission traces hydrogen gas energized by ultraviolet radiation from massive stars. It marks H2 regions, the active nurseries of the disk, where electrons recombine with protons and emit that characteristic red light. These regions are short-lived, because massive stars burn fast and explode. Their brief lifetimes make H-alpha a near real-time indicator of recent star formation. When we map H-alpha across Andromeda, we are essentially mapping where the last few million years left bright scars. The brightest knots are not just pretty, because they are places where the interstellar medium has been recently transformed. The H2 regions are also shaped by violence on small scales. Stellar winds carve bubbles and cavities, while radiation pressure pushes dust outward and sculpts bright rims. Supernova shocks sweep up shells that can trigger secondary collapse along their edges, turning destruction into a new round of creation. Even in a calm-looking spiral, the star-forming zones are turbulent, bright knots embedded in a churning medium. If we could hear them, the disk would not be silent. It would be a constant storm of expansion and collapse. Ultraviolet light traces young stars directly, especially those less embedded than the earliest phases. UV maps reveal where star formation happened over the last tens to hundreds of millions of years, long enough for clusters to drift from their birth clouds. The UV pattern can extend beyond the brightest optical arms, showing a broader star-forming disk than the eye expects. It also highlights clusters that are invisible in dustier optical views, because UV can be blocked, but also signals where dust is cleared. In UV, Andromeda's disk looks younger and more patchy, as if the galaxy is stippled with recent sparks. Infrared light reveals another organ of the system, the dust itself, and dust is more than a nuisance. Dust grains absorb ultraviolet and optical photons, then re-radiate the energy at longer wavelengths, turning hidden light into measurable heat. Infrared maps show where dust is thick and where it is heated, which often tracks star formation still wrapped in its natal cocoon. They also reveal embedded star formation that optical surveys miss, especially in the densest lanes. In the infrared, the galaxy's cold structure becomes luminous. Dark lanes turn into glowing filaments. The same features that obscure our view in one band become the brightest guides in another. Dust lanes are not only obstacles to seeing, because they are also reservoirs and conduits. They're tied to the cold gas that fuels future stars, and their shapes trace shocks, shear, and magnetic fields in the rotating disk. Where lanes bunch and curve, the disk's dynamics are actively sculpting the interstellar medium. The galaxy's visible beauty is a byproduct of hidden flows, and those flows are governed by gravity's quiet insistence. Even the lane thickness can hint at how gas is layered vertically, because the disk is not infinitely thin. A slight warp or flare can change how much dust lies along our line of sight, altering the apparent contrast. As we continue the pass, the disk reveals another signature that stands out across wavelengths. Andromeda's disk carries ring features that appear like ripples in a pond, but they are ripples in mass and star formation. The most prominent is the star-forming ring at roughly 10 kiloparsecs. It is not a perfect circle, and it is not merely decorative. It is a region where gas density and star formation are enhanced over a wide annulus. The ring acts like a scar and a signal, hinting at a past disturbance. It also acts like a boundary, separating inner regions that look older from outer regions that still form stars more actively. The ring's scale is difficult to appreciate until we translate it into plain terms. 10 kiloparsecs is tens of thousands of light-years, comparable to the span of our own galaxy's main star-forming regions. This is not a local bubble or a single spiral segment. It is a global rearrangement of gas, sustained long enough to leave a coherent imprint. When a feature encircles a galaxy at that scale, it forces us to ask what kind of event can push so much material into a shared rhythm. One origin story is a past interaction that sent a wave through the disk. A satellite passing through could drive a density ripple, piling gas into a ring as the wave propagates outward. Another possibility is a minor merger that reshaped the inner disk and redistributed gas, leaving the ring as a lingering resonance. The ring's persistence suggests a coherent dynamical cause, not random patchiness. Its existence pushes us to treat Andromeda as an evolving system, not a settled one. It also reminds us that even minor encounters can have major consequences when they perturb a delicate rotating disk. There is an important nuance in how such rings form. A passing companion does not need to destroy the disk to leave a lasting signature. A gravitational impulse can shift orbits slightly, and those shifts can crowd material into a ring-like overdensity. Over time, the disk's differential rotation stretches and smooths features, so a crisp ring implies either a strong event or a relatively recent one. The ring is therefore a clue about timing, because the galaxy's own rotation works to erase sharp patterns. Other ring-like structures and offsets complicate the picture. Some features look like nested rings or arcs, suggesting multiple episodes of disturbance rather than a single clean event. The disk may have been warped or tilted by tidal forces, changing where gas settles and where star formation ignites. Each ring is a constraint on timing, because patterns disperse unless continually maintained. The disk is therefore a clock as well as a map, and the clock is set by orbital periods. When we see an offset between rings and the central light, we are seeing dynamics that have not fully relaxed. As we move inward, the disk gives way to the bulge, and the tone changes. The light becomes smoother, more centrally concentrated, and less obviously structured, like fog thickening toward a city centre. Andromeda's bulge is unusually large and luminous compared to the Milky Way's. It is often described as classical, meaning it resembles an elliptical component embedded in a spiral. Classical bulges are typically built early, through rapid collapse or mergers. Their stars tend to be older, more metal-rich, and dynamically hotter. The bulge is where Andromeda looks less like a pinwheel and more like a compressed relic. Dynamically hotter is a technical phrase with a simple meaning. The stars move with larger random velocities, not just orderly rotation, so their orbits are more scrambled. That scrambling thickens the central region and erases delicate disk-like patterns. When we measure stellar motions in bulges, we are measuring how violently the centre was stirred. The bulge's smoothness is not calmness, because it can be the afterimage of ancient chaos. Bulge types matter because they encode formation pathways. A pseudo-bulge grows slowly from disk material, driven by bars and internal secular evolution that rearrange orbits over long times. A classical bulge points to violent early assembly, where gas and stars were stirred and concentrated. Andromeda's prominent bulge suggests an active early history, possibly including significant mergers. It implies that the galaxy's centre was shaped when the universe was younger and more chaotic. If we want to understand Andromeda's present, we have to respect how much of it was decided early. There is also a chemical clue embedded in bulge light. Older bulge stars often show enhanced abundances of elements made in rapid supernova explosions, especially those associated with short-lived massive stars. That pattern suggests fast early star formation, before slower enrichment channels had time to dominate. In other words, the bulge can carry a signature of speed, how quickly the galaxy built its central mass. Chemistry becomes a stopwatch, because different elements arrive on different schedules. The bulge also affects the present disk by deepening the central gravitational potential. A heavier bulge changes orbital frequencies and can influence bar formation and gas inflow, even if a bar is weak or absent. It can help funnel gas inward, feeding central star formation or a central black hole. Even when the centre looks quiet, its gravity organises the inner galaxy. The bulge is a structural anchor, but it is also a record of past upheaval. It is both weight and memory, concentrated into a bright core. Around and through these components, we find globular clusters, dense spheres of old stars. They orbit in the halo and sometimes through the outer bulge region, surviving as compact systems for billions of years. Their stars are packed tightly, so close that stellar encounters and long-term gravitational evolution can reshape the cluster from within. Globular clusters are valuable because their stars form together, sharing age and initial chemistry. That makes each cluster a dated sample of early conditions. They are like sealed layers in an archaeological dig, preserved against the erosion of time. Historically, globular clusters were among the first clues that galaxies have extended halos. Early 20th century astronomers used their distribution around the Milky Way to infer our galaxy's centre and scale, long before we could map the disk in detail. In Andromeda, they serve a similar role, but with a richer inventory and a broader range of properties. Each cluster is a tiny laboratory, where stellar evolution can be tested because distance and composition are shared. When we compare clusters, we are comparing snapshots of the early universe taken in different environments. Andromeda has a rich globular cluster system, often considered more numerous than the Milky Way's. The variety of cluster ages and metallicities suggests multiple formation episodes, rather than one monolithic burst. Some clusters are extremely old and metal-poor, likely formed early in small protogalactic fragments. Others are more metal-rich, implying formation in deeper potential wells or later enrichment. Some may have been accreted from dwarf galaxies that Andromeda later consumed. Their orbits can preserve that history, because accreted clusters often travel in coherent groups. A cluster's path can be as informative as its light. Metallicity acts as a chemical timestamp, because heavy elements build up over generations of stars. A metal-poor population formed before many supernovae enriched the gas when the universe was still chemically young. A metal-rich population formed after repeated cycles of starbirth and death, when the interstellar medium had been seasoned by earlier generations. By mapping metallicity across the disk, bulge, and halo, we reconstruct where enrichment happened fastest. The chemical gradient becomes a narrative of gas flows, star formation efficiency, and merger mixing. It also reveals where fresh metal-poor gas may have been added later, diluting the pattern. This chemistry is not abstract because it changes how stars form and evolve. Metals help gas cool by providing additional emission channels, and dust forms from heavy elements that condense in stellar outflows. A metal-rich environment can fragment differently, producing different stellar populations and different feedback. When we read metallicity, we are reading the conditions that shape the next generation. The galaxy's future is partly written by the chemical choices its past already made. Stellar populations also separate by age, and age separates by location. The disk contains young and intermediate-age stars, especially along spiral features and rings where gas is still abundant. The bulge is dominated by older stars, though it can host pockets of younger activity near the centre when gas finds its way inward. The halo is mostly old, but it is not uniform because accreted debris brings its own ages and compositions. The galaxy's anatomy is therefore a composite, assembled from different progenitors. It is less like a single organism grown from one seed and more like a mosaic built from many pieces. Now the disk's bright structure fades, and we enter the outskirts where the halo dominates. The stellar halo is faint and extended, far beyond the visible disk edge, and it is easy to miss without deep exposures. It contains sparse old stars and an even larger share of the galaxy's mass in dark matter. The halo is the region where Andromeda's growth history is most legible, because tidal debris survives longer in low-density space. In these outskirts, gravity writes slowly, and its handwriting stays readable. In deep surveys, the halo reveals streams, shells, and arcs of stars like pale smoke trails around a lantern. These are not random alignments, because their coherence requires a common origin and a shared orbit. They are the remains of dwarf galaxies torn apart by tides. As a dwarf falls in, gravity stretches it along its orbit, unbinding stars into a stream. Over time, the stream wraps and disperses, but it can remain visible for billions of years. The halo is therefore not empty background, because it is crowded with faint evidence. The mechanism is relentless and precise. The side of the dwarf closer to Andromeda feels a stronger pull than the far side. That difference, called a tidal force, elongates the dwarf and eventually exceeds its self-gravity. Once stars escape, they do not vanish. They continue along similar orbits, forming long, thin structures that trace the path of the destroyed system. The stream is a drawing made by gravity, using stars as ink. Shells and ripples suggest more radial encounters, where debris piles up near turning points and briefly slows before falling back. Streams suggest more elongated orbits, where debris traces a long path through the halo and gradually phase mixes. Each feature is a fossil record, preserving the orbit and mass of the disrupted system. By modelling these structures, we infer Andromeda's gravitational field. The halo becomes a laboratory for invisible mass, because the debris responds to gravity, not to light. In a sense, the streams are test particles, and the halo is the experiment. This is where the central question sharpens again. What secrets does Andromeda hold about formation and collision, if its faint outskirts are littered with remnants? The answer begins with the fact that galaxies grow by cannibalism. They accrete smaller systems, mix their stars, and keep the debris as long-term evidence. Andromeda's halo looks busy, implying a more active recent accretion history than the Milky Way's. If two neighbouring spirals can differ this much, what does that say about how common a quiet history really is? That comparison matters because it hints at different biographies for two neighbouring giants. If Andromeda has eaten more recently, its disk may be more perturbed, its bulge more massive, and its halo more structured. The sky's calm appearance can be misleading. Quiet light can hide a violent past. Even a galaxy that looks serene in a backyard telescope can be, in dynamical terms, a crime scene. The streams also connect to the ring features and bulge size. A significant interaction can disturb the disk, build or heat the bulge, and deposit debris into the halo. The same event can leave multiple signatures at different radii, each one fading on its own timescale. The challenge is to link them into one timeline. The suspense comes from incomplete evidence, because the most important mass component does not shine. We are reconstructing a story with missing pages, and the missing pages are the heaviest ones. To understand the hidden mass, we return to a basic measurement that has reshaped modern astronomy. We measure how fast stars and gas orbit as a function of radius, using Doppler shifts that reveal motion along our line of sight. In a system where most mass is concentrated near the centre, orbital speed should decline outward. That is what Keplerian intuition predicts from the solar system, where the Sun holds most of the mass. Yet galaxies do not behave that way, and the mismatch is not subtle. Andromeda's rotation curve stays high far beyond the bright disk. Gas and stars orbit too fast to be held by visible matter alone, even after we account for the mass of stars and cold gas. The implication is that mass continues to rise with radius, even where starlight fades into near darkness. Something unseen dominates the gravitational potential in the outskirts. The galaxy is embedded in a massive halo of dark matter. The luminous disk is not the whole machine, because the machine extends into invisibility. The historical weight of this realization is hard to overstate. By the late 20th century, rotation curves across many galaxies repeated the same message, and the pattern resisted easy dismissal. The luminous parts were not enough, and the discrepancy was systematic rather than accidental. Andromeda, close enough for detailed mapping, became one of the clearest demonstrations that the universe contains more than it shows. It helped turn a suspicion into a cornerstone of modern cosmology. Dark matter is not a substance we have touched, but its gravity is measurable. It acts like an invisible scaffold, shaping the disk's rotation and stabilizing the system against disruption. Without it, the outer disk would not remain bound at observed speeds, and satellite orbits would not look the way they do. The halo also influences how satellites orbit and how streams precess, bending their paths over time. We infer its shape and extent by fitting models to motions, then checking whether the same model explains multiple traces. When separate lines of evidence converge, the invisible becomes difficult to deny. The simplest picture is a roughly spherical dark matter halo extending far beyond the visible disk. Its density declines with radius, but its total mass is enormous, outweighing the stars by a wide margin. In this picture, stars are a bright frosting on a much larger dark structure. The halo's gravity sets the stage for galaxy formation, because it is the first component to collapse in the early universe. Gas falls into the dark potential well, cools, and forms the visible galaxy. The light is late, but the gravity comes first. This connects Andromeda's anatomy to formation theory. In the standard model, small dark matter clumps form first, then merge into larger halos as the cosmic web grows. Baryonic gas follows, but it can cool, shock, and lose energy in ways dark matter cannot. The disk forms as gas settles into rotation, conserving angular momentum while shedding heat. The bulge can form early through rapid collapse or later through mergers that scramble orbits. The details differ, but the scaffold remains the common foundation. If we understand the scaffold, we understand why certain structures are even possible. The halo streams fit naturally into hierarchical assembly. Each stream is a surviving trace of a smaller halo absorbed into a larger one, and each trace carries constraints on mass and orbit. The disk's rings and warps can be driven by these accretion events, even when the intruder is modest in mass. The bulge's size can reflect early major mergers or repeated minor ones that heat the center. The visible structure becomes a consequence of the dark scaffold's growth. The galaxy's beauty is therefore an emergent property of invisible architecture. Yet dark matter remains mysterious, and we must be careful about what we claim. We know what it does gravitationally, but we do not know what it is made of, and that gap matters. Several candidates compete, each constrained by experiments and by astrophysical observations. The mystery is productive because it forces new measurements and new theory. It also forces humility, because the dominant mass in a galaxy is still an inference. We are confident in its effects, but still ignorant of its identity. WIMPs were long a favoured candidate, heavy particles that interact weakly with normal matter. They would be abundant and stable, produced in the early universe in roughly the right amount, which made them especially attractive. Experiments have searched for their rare collisions with detectors on Earth, buried underground to shield them from cosmic rays. So far, those searches have not produced a definitive signal. The absence narrows the parameter space and pushes models toward new possibilities. In science, silence is not nothing, it is a constraint. Axions are another candidate, extremely light particles proposed for reasons that begin in particle physics. They could be produced copiously and behave as cold dark matter, clustering gravitationally despite their tiny mass. Their detection would require different strategies, often involving electromagnetic conversion in strong magnetic fields. Like WIMPs, axions remain hypothetical, but they fit within known physics extensions. Their appeal grows as other searches come up empty. The list of candidates shifts, but the gravitational evidence remains. Machos were a historical idea. Dark objects made of ordinary matter like faint stars or black holes. Surveys of gravitational microlensing show that such objects cannot make up most of the halo mass, because the lensing rate is too low. Big Bang nucleosynthesis and the cosmic microwave background also limit how much baryonic matter exists. The universe does not have enough normal matter to account for the missing mass. Dark matter must be largely non-baryonic, or our gravity theory must change. Either way, the implication is profound. Most of what holds galaxies together is not made of familiar stuff. Modified gravity ideas attempt the second route, changing the rules rather than adding matter. They can reproduce some galaxy rotation curves, but they struggle across all scales and across the full web of observations. Clusters, lensing, and the cosmic microwave background favour a dark matter component. For Andromeda, the simplest consistent explanation remains a dominant dark halo. The scaffold is invisible, but its fingerprints appear in many independent measurements. The galaxy behaves as if it is wrapped in mass we cannot see. Andromeda also contains another largely invisible component that matters for evolution. It is wrapped in a hot gas halo, part of the circumgalactic medium. This gas is tenuous and hot, detectable through X-rays and absorption lines against background sources. It extends far beyond the disk, occupying the same general volume as the dark halo. It is a reservoir and a boundary layer between galaxy and intergalactic space. It is also where a great deal of ordinary matter may be hiding. The temperatures in this halo are high enough that the gas emits weakly in X-rays, yet it is so diffuse that it can be difficult to image directly. Instead, astronomers often rely on absorption, watching how the halo imprints faint signatures on the light of distant quasars. Those signatures reveal ions that only exist in hot conditions, confirming that the space around the galaxy is not empty. The halo is an atmosphere, but it is also a history of inflow and outflow. Every absorption line is a faint testimony that the galaxy breathes. The CGM matters because it regulates star formation over long times. It stores baryons that never made it into stars, and it receives material blown out by supernovae and stellar winds. Gas can cool from the CGM and rain back onto the disk, replenishing fuel and extending the disk's active life. Gas can also be heated and prevented from cooling, starving the disk over time. The balance shapes a galaxy's future, even when the disk looks unchanged from one human lifetime to the next. The galaxy's pace is slow, but its accounting is strict. In Andromeda, the hot halo may contain a significant fraction of its missing baryons. It also interacts with satellite galaxies, stripping their gas as they orbit through this thin medium. That stripping can shut down star formation in dwarves, turning them into faint spheroidals that are rich in old stars but poor in gas. The CGM is therefore part of Andromeda's ecosystem, linking disk, satellites, and the larger environment. It is another layer we infer more than we see, and its invisibility makes it easy to underestimate. What looks like empty space is often the most consequential space. When we combine all these components, Andromeda begins to resemble a living organism in functional terms. The disk is the active tissue where new stars are born and die, and where gas is constantly processed into heavier elements. The rings and arms are circulation patterns that compress gas and trigger growth, leaving bright knots and dark lanes. The bulge is an older core, dense and dynamically hot, shaped by early violence. The globular clusters are preserved fossils carrying chemical and chronological tags. The halo is the memory field, storing streams and shells from past meals. Each part is distinct, yet each part depends on the others. And beneath all of it is the invisible scaffold, the dark matter halo that sets the gravitational rules. It holds the outer disk together, guides the orbits of satellites, and shapes the debris we use as evidence. It also links Andromeda to the cosmic web, because halos connect and merge along filaments that feed galaxies over time. The galaxy we see is only the luminous fraction of a much larger structure. The rest is inferred through motion, distortion, and faint absorption. We live in a universe where the dominant architecture is hidden, and we must learn to read its shadows. This is why anatomy builds suspense rather than closure. The brightest parts are the easiest to photograph, but they are not the dominant mass, and they are not the oldest evidence. The faint outskirts are hard to map, yet they preserve the clearest merger signatures because low densities slow the erasure of structure. The dark matter halo is essential, yet it refuses direct detection, remaining a conclusion rather than a specimen. Every layer we uncover points to a deeper layer we still cannot see. The more we learn, the more the unseen grows in importance. So we end this chapter with a map that is also a question. Streams, rings, and a heavy bulge imply a violent past, not a quiet spiral life. Rotation curves demand an unseen mass that outweighs the stars, and the demand is backed by repeated measurements. The hot halo hints at hidden baryons and future fuel constraints, suggesting that even a giant spiral can be limited by supply. Structure implies history, and history demands reconstruction. What, exactly, happened to make this spiral so massive, so scarred, and so surrounded by ghosts? Next, we turn anatomy into biography, using these clues to rebuild Andromeda's timeline. We follow the debris backward to the encounters that made it, and we test which stories fit all the evidence. We ask which mergers built the bulge, which passage drew the rings, and what the dark scaffold allowed. The smudge becomes a case file, and the galaxy becomes a story of growth through darkness. Next, we turn anatomy into biography, using faint evidence to rebuild deep time. We cannot watch billions of years unfold in real time, but we can read what remains in starlight, motion, and chemical fingerprints. Every star carries two kinds of memory: how it moves and what it's made of. Those memories are not poetic metaphors, they are physical records written by gravity and nuclear reactions. When we measure them carefully, we are not guessing at history, we're sampling the rules that shaped it. This is galactic archaeology, and the premise is strict. Gravity preserves patterns in orbits, even after the original bodies dissolve into a diffuse halo. Nuclear physics preserves patterns in chemistry, even after gas collapses into new generations of stars. If we measure both, we can infer the events that shaped Andromeda. The trick is patience, because the evidence is subtle, and the galaxy is far. Distance makes everything dimmer, and it also makes every measurement more vulnerable to confusion. On screen, Andromeda's bright disk dominates the view, a tilted lens of pale light with dark dust lanes. The dust cuts across the starlight like smoke in a spotlight, tracing cold gas where new stars may form. Yet the disk is only the visible centerpiece of a much larger structure, embedded in a halo of dark matter. That dark matter halo is unseen, but its gravity choreographs everything we can measure. The biography we want is written in that choreography. Even the disk's rotation curve, how fast stars orbit at different radii, whispers that most mass is hidden. The first clues live in the halo where time erases slowly. The disk mixes and smooths itself through rotation, scattering, and the restless pull of spiral structure. In the disk, stars orbit in a crowded environment, and small perturbations accumulate until patterns blur. Giant molecular clouds, spiral arms, and bars can all nudge stellar orbits, gradually heating and reshuffling the population. The halo is sparse, so tidal debris stays coherent longer. In the outskirts, Andromeda keeps its receipts. The halo is also where the contrast is hardest because the light is so thin. A single square degree of sky can contain countless foreground Milky Way stars, plus background galaxies masquerading as points. Some of those background galaxies are so compact that they mimic stars until deeper imaging reveals their shapes. To find Andromeda's halo, astronomers must separate signal from noise with statistical care. They do it by combining deep imaging with an understanding of stellar populations. The work is meticulous, because a small bias can invent a structure that is not truly there. Surveys began to map those outskirts with wide-field cameras and careful star counts. They separate Andromeda's stars from foreground Milky Way stars by colour and magnitude, exploiting how different populations trace different sequences. They use resolved red giants and horizontal branch traces to outline faint structures. Red giant branch stars are especially useful because they are bright enough to be seen at Andromeda's distance. Their colours also shift with metallicity, giving a first hint of chemical variation across the halo. The result is a halo that looks structured, not smooth. In visual terms, those maps resemble weather radar, wisps, arcs, and filaments emerging from a dark background. A smooth halo would look like a gentle gradient fading into space. Instead, Andromeda's outskirts show sharp edges and coherent streaks, as if something tore through and left threads behind. The eye is drawn to boundaries, because boundaries imply a recent disturbance. The halo does not merely surround the galaxy, it remembers. The most famous structure is the giant stellar stream. It is a long overdensity of stars extending far from the disk plane, curving like a pale ribbon through the halo. In deep renderings, it looks like frost on black glass, delicate but unmistakably patterned. Its stars share a common distance range and coherent velocities along the feature. That coherence implies a single progenitor, stretched by tides into a ribbon. Even when the stream fades in brightness, its kinematic signature stays crisp. A stream forms when a satellite galaxy falls into a larger potential well. The near side feels stronger gravity than the far side, and the satellite elongates under tidal forces. Stars escape near tidal radii and drift onto similar orbits, forming leading and trailing tails. Over time, the debris wraps, precesses, and phase mixes, but it remains detectable. What we see today is a snapshot of an ongoing unspooling. The stream is not a static monument, it is a moving flow. The physics is precise, even if the scene is ghostly. In a stable gravitational potential, stripped stars conserve energy and angular momentum approximately, so they trace a narrow path in phase space. Small differences in orbital period stretch the debris into long arcs, like beads sliding along a wire. Encounters with substructure can thicken or kink the stream, leaving secondary clues. Dark matter clumps, if present in sufficient numbers, can punch subtle gaps into the debris. A stream is therefore both a relic and a probe. The stream is not just a decoration, it is a dynamical measurement. Its curvature constrains the shape of Andromeda's gravitational field, including how flattened or spherical the halo might be. Its velocity gradient constrains the orbit of the disrupted satellite, telling us whether it plunged steeply or skimmed the outskirts. Its width and density constrain the satellite's mass and internal structure. A dense, compact progenitor sheds differently than a puffier dwarf. Even the stream's thickness can hint at how long the debris has been spreading. Astronomers also test whether the stream's stars share a common chemical signature. If the progenitor had its own enrichment history, the debris should carry a characteristic metallicity distribution. That distribution can be compared to known dwarfs and to Andromeda's smooth halo. When chemistry and dynamics agree, the reconstruction becomes harder to dismiss. When they disagree, the case becomes more interesting. Disagreement can mean multiple progenitors, or it can mean the halo itself has been mixed by earlier events. Other substructures complicate the map and deepen the story. Shells and arcs suggest debris piling up near orbital turning points, where stars slow and crowd together. Multiple streams suggest multiple accretion events with different orbits and times. Some features align with globular cluster groups, hinting at shared origins. The halo becomes a layered crime scene. Each layer is faint, but together they imply a long history of capture. Shells, in particular, carry a distinctive geometry. They can form when a satellite plunges in on a radial orbit, and its stars oscillate through the center like a thrown handful of stones. Each pass creates a new caustic, an edge where many orbits overlap, so the halo briefly looks like ripples on a pond. The ripples are not made of water, but of stars that once belonged to something else. Their sharpness tells us the disruption was not infinitely old. If the shells were ancient, phase mixing would have softened their edges into a blur. Globular clusters add another set of witnesses. These dense, ancient star swarms can survive tidal stripping and remain bound long after their host is shredded. If several clusters share similar orbits or lie along a stream, they may be former companions of the same accreted system. In Andromeda, the outer halo hosts many globular clusters, some unusually extended and faint. Their distribution hints that accretion built not only the halo's field stars, but also its cluster system. Clusters can also preserve chemical signatures that are easier to measure than those of individual faint stars. Dynamical models turn these patterns into timelines. Simulations drop satellites into Andromeda-like halos and evolve them forward, tracking how debris spreads in position and velocity. They match stream positions, distances, and line-of-sight velocities to find viable orbits. The best fits do not give certainty, but they narrow the family of past events. Each matches a constraint on Andromeda's mass profile. In effect, the stream becomes a test particle that has been running for billions of years. The modelling is also a lesson in humility. Small changes in the assumed halo shape can shift a stream's predicted track by degrees on the sky. Uncertainties in distance along the line of sight can blur the interpretation of curvature. Even the satellite's internal rotation can matter because it changes how stars are released. The biography is reconstructed, not recorded. That distinction matters because reconstructions must be revised when new data arrive. The tension rises because the evidence points beyond minor snacks. Andromeda's halo looks unusually rich in debris for a nearby spiral, with multiple prominent structures at large radii. Its bulge is large, and its disk shows signs of heating and disturbance. Even the stellar halo's brightness suggests a substantial mass of accreted stars, not just a few fragile dwarfs. These clues can be consistent with repeated minor mergers, but they also fit a bigger shock. The question becomes quantitative: how much mass arrived, and how quickly? A major merger is the possibility that changes the tone of the biography. A collision with a large galaxy several billion years ago would be transformative, reshaping both stars and gas. It could build a classical bulge by scrambling stellar orbits into a pressure-supported spheroid. It could thicken and heat the disk, leaving a calmer, smoother remnant. It could also fling stars outward, populating the halo with relatively metal-rich debris. The aftermath would not look like a wreck forever, because galaxies can relax into new equilibrium. Historically, this idea has been controversial because it challenges a simple visual intuition. When we see a grand spiral, we tend to imagine an unbroken, gentle history. Yet the modern view of galaxy formation is hierarchical, built from repeated mergers and accretion events. That framework matured as simulations improved, and deep surveys revealed distorted galaxies at earlier cosmic times. In that framework, a spiral can be a survivor, not a bystander. The question is whether Andromeda's spiral is a rebuilt structure. The idea sounds incompatible with Andromeda's present spiral form, but spirals can regrow. If enough gas remains or is later accreted, a new disk can settle as angular momentum reasserts itself. Simulations show disks rebuilding after violent encounters under the right conditions, especially when gas fractions are higher. A serene spiral can be the aftermath, not the absence of violence. The calm we see may be a late chapter. It invites a question that is almost unsettling. How many calm disks are actually second drafts? Gas is the key because gas can dissipate energy. Stars behave like collisionless particles, so they keep the heat of a merger and remain dynamically stirred. Gas, by contrast, can radiate away energy through cooling, collapse into a thin layer, and form new stars. That new stellar disk can look orderly even if an older population remains thickened underneath. The disk can therefore contain multiple dynamical ages at once. If we could watch and fast forward, we might see a messy collision resolve into a fresh, thin plane. Evidence for a major merger is indirect and therefore contested. The giant stellar stream may require a fairly massive progenitor, though not necessarily a full peer to Andromeda. The halo's metal-rich component is larger than expected from only tiny dwarfs, suggesting more substantial accretion. Some models link the disk's ring features and warps to a significant past impact. The bulge's prominence keeps the hypothesis alive. None of these clues is a confession on its own, but together they form a pattern worth testing. Even the rings invite interpretation. A ring can form from resonances inside a disk, but it can also be a density wave launched by an encounter. If a satellite plunged through the disk, it could generate expanding ripples in the gas, triggering star formation along a circular front. Over time, those ripples can persist as stellar structures, even after the intruder is gone. The challenge is to separate internal dynamics from external disturbance. The ring becomes a question posed in geometry. Was it sculpted from within or struck from without? To test such ideas, astronomers use chemistry as a second independent archive. In astronomy, metals means every element heavier than helium, a definition that surprises newcomers. Hydrogen and helium came mostly from the Big Bang, with only trace lithium. Metals were forged later inside stars and distributed by winds and supernovae. Every oxygen atom in a rock, every iron atom in blood, began as stellar ash. When we map metals in Andromeda, we are mapping the accumulated work of countless dead stars. Metals matter because they trace how many stellar generations came before. A metal-poor star formed early, from gas with little prior enrichment, so it is chemically primitive. A metal-rich star formed later, after repeated cycles of starbirth and death enrich the interstellar medium. Metallicity becomes a proxy for time and environment, with caveats. A star can be old and metal-rich if it formed in a deep potential well that enriched quickly. The same number can therefore point to different histories depending on where the star was born. Astronomers quantify metallicity using logarithmic measures like FeH, comparing iron abundance to the Sun. A value of -1 means 1/10 solar iron, while -2 means 1/100th. This scale compresses enormous ranges into manageable numbers, but it also hides complexity. Iron is only one element, and different nucleosynthetic channels can decouple iron from other metals. That is why ratios matter. In a sense, metallicity is the headline, while element ratios are the fine print. Chemical tagging goes beyond total metallicity and looks at element ratios. Alpha elements like oxygen, magnesium, and silicon are made efficiently in core collapse supernovae, the deaths of massive stars. Iron builds up strongly in Type Ia supernovae, which occur on longer delay times as white dwarfs ignite. The alpha-to-iron ratio therefore tracks the pace of star formation. It is, in effect, a clock with a built-in lag. That lag is physical, set by stellar lifetimes, not by our choice of model. If star formation is rapid, alpha elements rise before Type Ia iron arrives, leaving a high alpha-to-iron signature. If star formation is extended, iron catches up and alpha ratios decline as Type Ia events accumulate. So a high alpha-to-iron pattern implies fast early build-up, often in dense environments. A lower alpha-to-iron pattern implies slower, more prolonged enrichment, typical of small dwarfs. The pattern is a chemical narrative of tempo. It tells us not only what formed, but how quickly it formed. Spectroscopy makes this possible by splitting starlight into its component wavelengths. Dark absorption lines appear where elements in a star's atmosphere absorb specific colours, each line a fingerprint. Measuring line strengths requires careful calibration, because temperature and surface gravity also affect the spectrum. For Andromeda, this work is demanding, since individual stars are faint and crowded. Sky background, atmospheric absorption, and instrumental effects all have to be modelled away. Yet with large telescopes and multi-object spectrographs, the sample sizes have grown. With each new sample, the halo's chemistry becomes less anecdote and more census. In Andromeda, metallicity varies across bulge, disk, and halo. The inner regions are metal-rich, consistent with deep potential wells and efficient early enrichment, where gas was retained and recycled. The outer halo includes metal-poor stars typical of accreted dwarfs, which enriched slowly and lost metals to winds. Yet there is also a surprisingly metal-rich halo component, suggesting accretion of larger systems or strong early mixing. That mixture is a clue to Andromeda's appetite. It hints that some meals were not small. Gradients matter because mergers disturb them. A quiet disk can maintain a smooth radial metallicity gradient over time, with inner regions richer than the outskirts. A merger can mix stars and gas, flattening gradients and scattering metal-rich stars outward into the halo. It can also drive gas inward, steepening central enrichment while diluting outer regions. So the present chemical map constrains how violently Andromeda was stirred. The gradient is a scar that can fade but not vanish. If we read it correctly, it tells us where the galaxy has been shaken. There is also a vertical dimension to the chemistry. Thick disks in many galaxies tend to be older and more alpha-enhanced, reflecting rapid early star formation. Thin disks are often younger and less alpha-rich, built over longer times. If Andromeda's disk was heated or rebuilt, the alpha patterns should record that shift. chemistry becomes a way to separate overlapping populations that look similar in images. It is a reminder that a galaxy can look smooth while still being stratified in time. Chemistry alone cannot date a single star precisely, so astronomers add age dating. For Andromeda, this requires resolving individual stars, not just measuring blended light, because integrated spectra blur ages together. The Hubble Space Telescope makes that possible in selected fields, even though Andromeda is more than 2 million light-years away. It turns Andromeda from a smear into a population diagram. In that diagram, each dot is a star with a story. The act of resolving them feels like lifting fog off a landscape. The key tool is the colour magnitude diagram, a census of brightness versus colour. Stellar evolution predicts where stars of different masses and ages should sit, because a star's luminosity and temperature change as it burns fuel. The main sequence turn-off is especially powerful because it shifts with age as the most massive surviving stars peel away. By fitting models to the diagram, astronomers reconstruct star formation history. It is like reading tree rings, but in the language of physics. And like tree rings, the record can be interrupted by storms. On screen, a colour magnitude diagram looks abstract at first. An angled plume, a dense band, a hooked turn-off. Yet each feature has meaning. The red giant branch traces stars that exhausted core hydrogen and expanded, a late-life phase for many masses. The horizontal branch reflects helium burning and is sensitive to age and metallicity. The turn-off is the timestamp because it marks how long stars have been shining. When we focus on the turn-off, we are focusing on the slow ticking of stellar lifetimes. HST fields across Andromeda reveal a complex timeline. The bulge is dominated by old stars, but it is not purely ancient, suggesting multiple episodes of formation. The disk shows extended star formation, with variations by radius and ring structures that hint at dynamical triggers. The halo contains very old populations plus intermediate-age debris, consistent with accretion over time. In some fields, the mix implies that Andromeda kept forming stars while also swallowing smaller systems. The galaxy is not one population, but many layered populations. Age dating also tests the merger hypothesis in a specific way. A major merger can trigger a burst of star formation by compressing gas in shocks and tidal inflows. It can also quench star formation temporarily by heating or expelling gas, depending on feedback and gas supply. If Andromeda had such an event, the star formation history may show a distinctive bump or shift. The difficulty is that real galaxies rarely provide clean single-peak signatures. A burst can be smeared across time by mixing, and it can vary from one region to another. The evidence suggests significant activity several billion years ago, though the interpretation remains debated. Some reconstructions find enhanced star formation in that window across large regions, consistent with a global disturbance. Others argue the signal can arise from secular evolution and minor interactions, including bar-driven inflows and repeated small impacts. The uncertainty keeps the biography open, and that openness drives the narrative. In science, ambiguity is not failure, it is a map of what to measure next. It also forces a deeper question: what would count as decisive evidence in a system this complex? Now the story turns from debris to companions, because some actors survived. Andromeda's satellite system includes M32 and NGC 205, plus many dwarf spheroidals scattered through the halo. These satellites are not just neighbours, they are ongoing experiments in tidal physics. Their shapes, gas content, and star formation histories show what Andromeda does to smaller galaxies. They also show what those smaller galaxies do in return. Each satellite is a laboratory where gravity runs the same experiment under slightly different initial conditions. The local group context matters here, because Andromeda is not isolated. The Milky Way and Andromeda dominate the group's gravity, and their satellite systems may have been shaped by shared history. Some satellites could have been exchanged or perturbed during past interactions. Even without direct contact, the large-scale environment influences infall directions along filaments. The satellites are therefore both local and cosmological clues. Their orbits are like arrows pointing back toward the routes by which matter entered the group. M32 is compact and unusual, and its origin is still argued. It could be a stripped remnant of a larger galaxy, peeled down to a dense core by Andromeda's tides. If that happened, the missing outer stars might be scattered into the halo as diffuse light or streams. It could also be intrinsically compact, shaped by early formation and later tides. Either way, Its proximity makes it a clue to past interactions. A stripped origin would also help explain why it looks so dense compared to typical dwarfs. Visually, M32 looks like a bright, smooth oval pressed against Andromeda's disk, almost too neat to be accidental. Its high surface brightness suggests a dense stellar system, packed into a small volume. If it was stripped, then the stripping must have been efficient and repeated, requiring close passages. That would imply an orbit that threads through Andromeda's inner regions, dangerous territory for a small galaxy. The scene invites a quiet question. How many close passages can a satellite survive before it becomes only a stream? NGC 205 shows signs of tidal disturbance and complex star formation. Its outer isophotes look stretched, and its internal populations include younger stars than typical dwarf spheroidals. It has experienced gas loss and morphological transformation, moving along the path from gas-rich to gas-poor. Tidal forces stretch stellar distributions and can pull out streams. Ram pressure stripping by Andromeda's hot halo can remove gas, shutting down future star formation. In a single companion, we can watch both gravity and gas physics at work. Ram pressure is a simple idea with dramatic consequences. As a satellite plows through hot, diffuse halo gas, it feels a wind, and that wind can push its own gas out. If the satellite's gravity cannot hold the gas against that pressure, the gas is stripped away and star formation fades. The stars remain, but the future is removed. In that sense, Andromeda does not only eat galaxies, it can starve them. The process also seeds Andromeda's halo with stripped gas that may later cool or mix. The dwarf spheroidals extend the pattern across the halo. Many are gas-poor and dominated by old stars, consistent with environmental quenching and early gas loss. Their orbits determine how strongly tides and hot gas act on them, and those orbits are often inferred rather than directly measured. Each dwarf is a test of Andromeda's mass distribution and its circumgalactic medium. Their survival also constrains how dense Andromeda's inner halo can be. If the inner halo were too destructive, more dwarfs would already be gone. A deeper puzzle emerges when we look at satellite positions in 3 dimensions. Some satellites appear to lie in thin, coherent planes, with hints of shared motion. Similar planar alignments are claimed around the Milky Way, which makes the pattern harder to ignore. If real and long-lived, these planes challenge simple expectations from random accretion. They force us to ask whether we are seeing structure or seeing coincidence. They also force us to confront how incomplete our surveys still are at the faintest limits. Several explanations compete, and none is settled. The planes could be transient alignments amplified by selection effects, because we detect some satellites more easily than others. They could reflect group infall, where satellites arrived together along a filament and retained correlated orbits. They could be tidal dwarfs formed in past interactions, though that raises dark matter questions. The mystery remains an open door in the case file. If the planes persist, they may be telling us something about how the local group assembled. That open door matters because it touches a larger theme. Cosmological simulations predict that satellites arrive along filaments, so some anisotropy is expected. Yet extremely thin planes, if persistent, are harder to produce and keep stable. Are we catching a temporary arrangement, like birds briefly forming a line in the sky? Or are we missing a piece of the physics that organizes small galaxies? The question is unsettling, because it sits at the boundary between data limits and theory limits. Triangulum, M33, adds another layer of uncertainty and potential drama. M33 is smaller than Andromeda, but massive enough to matter dynamically, with its own disk and star-forming regions. A past-close passage could warp Andromeda's disk and disturb M33 itself, leaving signatures in both galaxies. Some models use this interaction to explain features like warps and rings. Others treat M33 as a distant companion, whose influence is limited. The debate turns on tiny motions measured across enormous distances. On screen, M33 appears as a delicate spiral, more open and ragged than Andromeda, with bright knots of star formation. Those knots are giant H2 regions, clouds of ionized hydrogen lit by young, massive stars. The glow is not just pretty, it is diagnostic. Ionization requires short-lived stars, so it marks recent activity. If M33 was tugged hard, its gas disk should show it: warps, asymmetries, and disturbed outer structure. The galaxy's present shape becomes a witness to its past trajectory. Orbital histories are inferred from proper motions, distances, and dynamical modelling. Proper motion is tiny at these distances, so measurements are difficult and error bars matter, even with the best instruments. HST and radio interferometry provide constraints, but not a single definitive orbit. Different assumptions about halo mass and tangential velocity change the path dramatically. A heavier halo pulls harder, tightening the orbit and increasing the chance of a close pass. In this sense, the orbit of M33 is also a measurement of Andromeda's hidden mass. In one family of models, M33 passed close to Andromeda a few billion years ago. That encounter could excite warps and drive gas inflows, potentially enhancing star formation in rings. It could also strip material and seed halo substructure, adding another layer to the debris field. In another family of models, M33 never came close, and the disturbances require other culprits. The same present-day snapshot can support multiple histories. That is the strange power of deep time. Many paths can lead to the same present. We treat that uncertainty as narrative engine rather than weakness. The Galaxy's biography is not a single photograph, it is a reconstruction assembled from partial evidence. Every new measurement tightens some parameters and loosens others, because the constraints interact. The suspense is scientific, because the answer changes how we generalize galaxy evolution. If Andromeda is merger-scarred, spirals everywhere may be more fragile than they look. And if it is not, then our own Milky Way may be the less typical sibling. The centre of Andromeda carries a different kind of clue, a quiet engine. At its core sits a supermassive black hole often called M31N, embedded in a dense nuclear region. Its mass is large, comparable to or larger than the Milky Way's central black hole, which anchors our comparisons. Yet it is relatively dim, which is itself information. A massive black hole can be nearly invisible if it is not being fed. In the darkest images, the nucleus looks calm, yet the gravity there is extreme. A black hole is dark unless it is fed. Accretion converts gravitational energy into heat and radiation as gas spirals inward, compressing and frictionally heating in an accretion flow. If gas supply is low, the accretion flow is weak and radiatively inefficient, producing little light. The black hole can exist in near silence for long periods. Silence, in this context, is a measurement of scarcity. It also hints that the inner galaxy may currently be short on cold gas. When accretion is strong, black holes can launch jets and power active galactic nuclei. Jets are collimated outflows driven by magnetic fields and rotating accretion disks, and they can extend far beyond the galaxy's core. They can heat surrounding gas and regulate star formation by feedback, preventing too much gas from cooling at once. In Andromeda, the lack of strong activity suggests limited fuel, not a small black hole. The engine is large, but the tank is low. The contrast reminds us that black hole mass and black hole brightness are not the same thing. The quiet center still emits in subtle ways, including radio and X-ray signatures that flicker with time. Those emissions help constrain accretion physics in a low luminosity regime, where the flow may be hot and tenuous. They also remind us that central engines can switch states over cosmic time, responding to changing fuel supply. A past merger could have delivered gas and briefly awakened the nucleus. If so, the outburst may have left faint imprints in surrounding gas. Even a short-lived flare can rearrange the inner environment. Beyond the nucleus, Andromeda is rich in compact objects that shine intermittently. X-ray binaries are systems where a neutron star or black hole accretes from a companion, often through a disk. The accretion disk heats to millions of degrees and emits X-rays, making these systems visible across the galaxy. Some are persistent, others are transient, flaring when accretion rates spike. Each flare is a reminder that stellar death can power new light. In X-rays, the galaxy's quiet optical face becomes a field of sudden beacons. Andromeda is close enough to study X-ray populations across different environments, from the crowded bulge to the structured disk. In the bulge, many X-ray binaries are old systems, linked to ancient stellar populations and dense stellar interactions. In the disk, some are younger, tied to recent star formation and massive stars that evolve quickly. Comparing these populations tests how binaries form, evolve, and survive in different densities. It also links stellar demographics to galactic history. The distribution of X-ray sources becomes another kind of map, one drawn by remnants. Compact objects connect the biography to recycling of matter. Massive stars explode as supernovae, enriching gas with metals and injecting energy that stirs the interstellar medium. neutron stars and black holes remain, often in binaries that continue to influence their surroundings through radiation and winds. The galaxy's chemical evolution is therefore linked to its graveyard. In a sense, the halo's metals and the bulge's remnants are chapters of the same book. The living and the dead are not separate populations, they are stages of the same cycle. Now we widen the frame again, because mergers are not the only growth channel. Galaxies are fed by the cosmic web through gas inflow and minor accretion, a slow supply line from intergalactic space. Cold or warm gas can stream along filaments into halos, then cool into disks when conditions allow. This supply can sustain star formation long after initial gas would have been consumed. Without replenishment, even a spiral would eventually run out of fuel. The question is not whether inflow happens, but how efficiently it becomes new stars. The circumgalactic medium, the hot diffuse gas around a galaxy, plays a central role here. It can store baryons, exchange material with the disk, and respond to feedback from stars and black holes. If the halo gas is too hot, cooling is slow and the disk starves. If cooling is efficient, gas rains back down and forms new stars. The balance between heating and cooling shapes the galaxy's long-term colour and brightness. In Andromeda, that balance may be tipping toward quiet. Andromeda's present star formation rate is modest compared to some spirals, and its disk looks less vigorously blue than galaxies in full bloom. That could reflect limited fresh inflow, stronger heating in the halo, or past events that reduced cold gas. Quenching mechanisms include gas exhaustion, feedback heating, and environmental stripping, and they can operate together. The balance determines whether a spiral stays blue and active, or reddens into quiet. Andromeda seems to hover in that transition zone. It looks like a galaxy deciding slowly what it will become. Minor mergers also contribute without destroying the disk. They add stars to the halo and thicken the disk through repeated perturbations, a slow accumulation of dynamical heat. They can deliver gas that reignites star formation in rings and outer regions, especially if the gas arrives with misaligned angular momentum. Over billions of years, many small events can mimic some signatures of one large event. That is why the case is difficult, and why it is worth pursuing. The halo's complexity may be telling us that Andromeda grew by more than one method. So the biography becomes a problem of distinguishing pathways. Do Andromeda's scars require a single major merger, or many smaller ones that add up over time? Do its rings and warps point to M33, to a swallowed satellite, or to internal dynamics amplified by chance? The answer matters because Andromeda is our nearest large comparison, and our theories must fit both neighbours. If the two big spirals differ, we need to know why. And if they are similar, we need to know what hides that similarity. We return to the central question with sharper edges. What secrets does Andromeda hold about how galaxies form, evolve, and collide? It holds the secret that calm appearance can be a late chapter, not the whole book. It also raises a quieter question. How many galaxies around us are similarly rebuilt, wearing order as a disguise? If we can decode its hidden history, we learn how common violence is in spiral lives. We also learn how often the universe rewrites its own structures. The evidence we have is faint, and that faintness is part of the mood. Streams are low contrast and easily missed without deep surveys that push into the background noise. Chemical patterns require large spectroscopic samples and careful calibration across instruments and models. Proper motions require years of baseline and exquisite stability, because the sky shifts are smaller than a pixel. The biography is written in whispers, not headlines. And yet whispers can be consistent if we listen long enough. Yet the direction of the story is clear even when details are contested. Andromeda grew by accretion, and its halo preserves multiple events in overlapping layers. Its bulge and disturbed structures suggest significant past heating, whether from one impact or many. Its satellites are being stripped and transformed in real time, showing the process still underway. The galaxy is not finished with change. It is still collecting, still mixing, and still responding to gravity's long reach. And the final beat of this chapter is a bridge to what comes next. If Andromeda's past is written in collisions, its future is too, because it is already moving toward us. The ghosts in its halo are previews of what will happen when two giant disks finally meet. The same physics that drew in small satellites will, on a larger scale, draw the local group's giants together. The question is no longer whether gravity will act, but how the encounter will unfold. Next, we leave reconstruction and face prediction. following the orbit that brings Andromeda closer each moment. The story shifts from reconstruction to prediction, because Andromeda is not only a relic, it is a moving mass, and its motion is already measured against our sky. In earlier chapters, we treated it like a fossil record. Now it becomes a clock. The same light that carries its history also carries its trajectory, and that trajectory points back toward us. This is one of astronomy's quiet miracles, because the evidence arrives without engines or probes. Photons leave Andromeda, cross a gulf of space, and reach our telescopes carrying two messages at once. One message is what Andromeda was, when the light began its journey. The other message is what Andromeda is doing now, how fast it is moving, and in what direction. Astronomers start with the simplest component, the line of sight speed, because it is written directly into the spectrum. Andromeda's light is blue-shifted, showing a radial approach near 110 km per second. The effect is the Doppler shift in its cleanest form, wavelengths compressed as the source moves toward the observer. It is stable across instruments and decades, because the physics is simple and the signature is repeatable. In a spectrum, that signature appears as a systematic displacement of familiar lines, like a musical score transposed to a higher key. Calcium absorption, hydrogen features, and narrow lines from interstellar gas all slide together. The shift is tiny in fractional terms, yet modern spectrographs can resolve it cleanly. In plain language, the entire pattern is nudged toward the blue, and the amount of that nudge becomes a speed. In practice, scientists do not measure one line and stop. They compare many absorption features from stars and gas, cross-correlating patterns to reduce noise. They correct for Earth's orbit, Earth's rotation, and the Sun's own motion around the Milky Way. Each correction is small, yet each one matters, because precision is the difference between a vague approach and a mapped future. Those corrections are not bookkeeping for its own sake, because our vantage point is in motion at multiple scales. Earth spins at hundreds of meters per second at the equator, and it orbits the Sun at about 30 kilometers per second. The Sun itself streams around the Milky Way at roughly 220 kilometers per second, and the Milky Way drifts within the local group. When astronomers subtract these layers, they are peeling away our own movement to reveal Andromeda's. Yet a collision requires more than approach along our line of sight. We also need the sideways drift, the tangential motion that barely changes position over years. A galaxy can be coming toward us and still miss, sliding past like two ships in fog. The missing piece is proper motion, the slow crawl of Andromeda across the background sky. Proper motion is familiar for nearby stars where it can be measured in arc-seconds per year. For Andromeda, the same concept becomes almost surreal, because the distance is so immense. The galaxy is roughly 2.5 million light-years away, so even a substantial sideways speed becomes a vanishingly small angular shift. The geometry is ruthless, double the distance, and the apparent motion shrinks by half. At 2.5 million light-years, even a fast transverse speed becomes a tiny proper motion. A few tens of kilometers per second sideways translates into micro-arc-seconds per year. That is like watching a human hair move by the width of a bacterium from thousands of kilometers away. The numbers are real, but they live at the edge of what measurement can hold. The challenge is scale, because the signal is micro-arc-seconds per year. That is smaller than a pixel shift on most detectors, and smaller than atmospheric distortion from the ground. Even space telescopes must contend with thermal flexing, detector geometry, and subtle changes in focus. The measurement becomes a test of instrument stability, reference frames, and patience. The patience matters because proper motion is not a snapshot, it is a baseline. A single image freezes a moment, but it cannot reveal drift without a second moment to compare. Years must pass, and the same field must be revisited, with nearly identical pointing and calibration. The long wait is part of the instrument, because time itself becomes the lever arm. There is also the problem of what exactly is being tracked. Andromeda is not a rigid plate sliding across the sky. Its stars orbit, its disk is tilted, and its halo is extended and lumpy. A proper motion measurement must average over internal motions, which can masquerade as drift if the sampling is uneven. Even within a small patch of Andromeda's disk, stars have their own velocities, and gas clouds do not sit still. The galaxy rotates, and its satellite system adds additional complexity in the outskirts. If a measurement favors one region over another, internal rotation can bias the inferred shift. The solution is statistical: measure many stars, model the internal kinematics, and isolate the net motion of the whole system. Hubble's Space Telescope provided one route to the answer. HST tracked Andromeda's motion against distant background galaxies, using them as nearly fixed markers. Those background galaxies are so far away that their own proper motions are effectively zero on human timescales. In the images, they become the pins in a cosmic map, while Andromeda's field of stars becomes the moving sheet. The method is conceptually simple, but technically unforgiving. Hubble must return to the same field years apart, align the frames, and model the detector's distortions at the sub-pixel level. Even the point spread function, the way starlight spreads on the camera, must be characterized because its asymmetries can bias centroids. Over long baselines, the tiny shift accumulates into a measurable constraint. The deep trick is that the background galaxies are not perfect points, and their shapes complicate centroiding. Astronomers build careful models of how the camera maps the sky, including subtle warps across the field. They also track how the optics change with temperature and time, because even a minute flex can imitate motion. When the analysis is done, the measurement is not a single arrow but a probability cloud. Gaia provides the second route by mapping the Milky Way stars with extreme precision. Gaia refines our own motion through space, which must be subtracted from any apparent drift. It also improves the inertial reference frame that anchors proper motion work. In effect, Gaia tells us how our observing platform is moving, so Andromeda's motion is not confused with ours. Gaia's achievement is not only accuracy, but coherence. It ties positions, parallaxes, and proper motions into a single global solution. That solution is anchored to distant quasars, whose light comes from the early universe and barely shifts at all. When Gaia improves the reference frame, it improves every measurement built upon it, including the delicate inference of Andromeda's sideways speed. There is history behind this, because astronomy has always depended on reference frames that grow more stable over time. Early star catalogues were limited by the human eye and mechanical instruments, and even small systematic errors could ripple through decades of work. Gaia is a modern answer to an old problem, turning the sky into a rigid grid with well-characterized uncertainties. It is not just a map, but a foundation. Together, HST and Gaia narrow the allowed tangential velocity. The best constraints imply Andromeda is not just passing by, and not orbiting safely at large impact parameter. The most likely trajectory points toward a future close encounter. The allowed sideways motion is small enough that gravity has time to pull the two systems inward, rather than letting them slip apart. In orbital terms, the question is whether the Milky Way and Andromeda are on a bound path that will decay. A large tangential speed would imply a wide swing, perhaps even a flyby. A small tangential speed implies a more direct approach, where the overlap of halos becomes inevitable. The data do not give a single fate with no ambiguity, yet they strongly favour a merger. This is where gravity confronts cosmic expansion, and the confrontation is often misunderstood. The universe expands, and distant galaxies recede with the Hubble flow. Yet expansion is not a force that pulls objects apart like a stretched rubber sheet. It is a description of how space itself evolves on large scales, and local gravity can overwhelm it. A useful way to picture it is to separate the smooth background from the clumps. The background expands, and the average distance between unbound regions grows. The clumps, galaxies, groups, clusters, are places where matter has already collapsed into deeper gravitational wells. Inside those wells, the expansion is not the dominant term in the accounting. Bound systems ignore the Hubble flow because their self-gravity dominates locally. The local group is a gravitational island, decoupled from expansion on these scales. Milky Way and Andromeda sit in a shared dark matter environment that keeps them bound. If you could see that environment, it would look like an overlapping fog of mass, deeper than the visible disks. That fog is not poetic license, because dark matter halos are extended and diffuse. They do not end at the bright edge of a spiral disk, and they do not stop where the starlight fades. Their density declines with radius, yet their reach is vast, and their total mass dominates the gravitational potential. The visible galaxies are the bright cores of much larger structures. Historically, this idea came into focus as astronomers realized galaxies rotate too fast for their visible matter. The missing mass, dark matter, was inferred from rotation curves, galaxy clusters, and later from gravitational lensing. In our case, The dark halos are not a footnote, they are the main stage because they carry most of the mass that sets the orbit. The rotation curve story has a lineage, from early hints to the decisive measurements that made the discrepancy undeniable. When astronomers plotted orbital speed versus radius, they expected the curve to fall like planets around the Sun. Instead, the speed stayed high far into the outskirts, implying unseen mass spread through the halo. That same unseen mass now determines how two galaxies tug on each other across millions of light years. The local group's mass is the key, because gravity sets the long-term orbit. Dark matter halos overlap, and their mutual pull grows as separation shrinks. The halos are extended, reaching far beyond the bright disks, and they begin interacting long before the stars do. Expansion matters for the cosmic web, but it does not rescue neighbours already tied together. There is a useful plain language way to say it. The Hubble flow wins when gravity is weak and distances are vast. Gravity wins when mass is concentrated and the system is already bound. The Milky Way and Andromeda are in the second category, and their future is written in that difference. So the prophecy becomes a timeline, built from measured motion and modelled mass. Current models place the first close pass around 4 to 5 billion years from now. The uncertainty remains real because tangential speed and halo mass still carry error bars. Small changes in sideways velocity can shift the closest approach by tens of thousands of light years. Those models do not rely on hand-waving because they are tested against what we already observe. They must reproduce the present separation, the measured radial approach, and the plausible mass distribution of the local group. They also include the gravitational influence of Andromeda's companions and the Milky Way's satellites, which add subtle perturbations. The future is computed as an ensemble of possibilities, not a single scripted scene. The timescale is long, but the direction is fixed. Every second, Andromeda is closer by roughly 100 kilometers along our line of sight. The approach is slow to human senses, but relentless in gravitational accounting. Even a tiny inward drift, integrated over billions of years, becomes a meeting. It helps to imagine the local group as a quiet basin. 2 heavy stones sit on its floor, and the basin is the combined gravitational potential. Over time, the stones slide toward the deepest point, not because of drama, but because the geometry demands it. The future is not a sudden crash, but a long descent. We clarify what the word collision means in a galaxy, because the everyday meaning misleads us. A galaxy is mostly empty space, with stars separated by light years. Even in a dense disk, the chance of direct star-star impact is extremely small. The scale is so sparse that 2 galaxies can overlap and still have almost no physical contact between stars. If you could shrink a star to the size of a grain of sand, the typical spacing would still be kilometers. That emptiness is why galaxies can interpenetrate, and why the drama is gravitational rather than mechanical. The stars keep moving, each following its own orbit through a changing potential. What changes is the map of those orbits. Stars behave like collisionless particles in this encounter. They pass through the changing gravitational field, and their orbits are deflected rather than physically smashed. The real collision is between potentials, not between stellar surfaces. Gravity is the sculptor, and the stars are the grains of sand it rearranges. That does not mean nothing happens. Gravity has gradients, and gradients are where structure is rewritten. As the galaxies near, the near sides feel a stronger pull than the far sides. That differential force stretches disks, heats stellar motions, and pulls out long tidal tails. The word tidal is the same one we use for oceans because the mechanism is the same. Tides are a geometric consequence of gravity's inverse square law. When one side of a galaxy is closer to the other's mass, it accelerates slightly more strongly. Over hundreds of thousands of light years, that small difference becomes a powerful shear. The disk responds by elongating, warping, and shedding material into extended streams. The first close pass is not a clean hit, but a near miss with consequences. The disks interpenetrate in projection, and the halos overlap deeply. Orbits are scrambled, and the familiar spiral order begins to loosen. The arms that once traced steady rotation become distorted, and the disk thickens as stars are kicked into higher, puffier paths. In simulations, the first approach often produces a moment of eerie beauty. 2 luminous spirals swing past, their cores bright and compact while their outer disks stretch like pulled taffy. Dust lanes twist into arcs, and star-forming regions flare in compressed ridges. The scene is silent, but the dynamics are violent in slow motion. The beauty is not decorative because it encodes physics you can read. The length and curvature of tidal tails depend on the encounter geometry and the depth of each halo. The timing of star formation depends on how gas responds to shocks and torques. Even the survival of a disk depends on how much orbital energy is deposited into random stellar motion. Tidal tails form as stars are flung outward along elongated paths. Some material becomes unbound, escaping into intergalactic space within the local group. Other material remains bound but displaced, populating an expanded halo and faint streams. These streams can persist for billions of years, like scars that do not heal. The encounter also produces bridges and shells depending on geometry and impact parameter. Bridges are transient connections of stars and gas, drawn out between the galaxies as they trade material. Shells are ripples, often seen in elliptical remnants, created when stars pile up at turning points in their new orbits. These structures are the same physics we used to read Andromeda's past. Now we watch that archaeology being written in advance. After the first pass, the galaxies do not simply separate forever. Dynamical friction drains orbital energy as each galaxy moves through the other's dark matter halo. The effect is subtle in a single moment, yet powerful over time. It is like moving through a sea of particles that gravitationally tug back, creating a wake that saps momentum. That wake is a real overdensity, a slight piling up of dark matter and stars behind the moving galaxy. The wake's gravity pulls backward, converting orbital motion into heat in the halo. Over many orbits, the energy loss accumulates, and the separation at each apocenter shrinks. The galaxies return again, not by chance, but because the orbit is being braked. The orbit decays, and the pair returns for subsequent encounters. These later passes can occur over hundreds of millions to a few billion years. Each pass further heats the disks and transfers angular momentum outward. The system oscillates, like a ringing bell that slowly loses energy. This is where the concept of angular momentum becomes visible. A spiral galaxy is an ordered system, with many stars sharing a preferred direction of rotation. A merger converts some of that order into random motion, because gravitational torques redistribute energy and momentum. The result is not destruction, but transformation. Order becomes dispersion. Torques arise because the mass distribution is no longer symmetric. As the galaxies distort, their gravitational pull becomes lopsided, and that lopsidedness pushes and pulls on orbits. Some stars gain angular momentum and move outward into extended tails. Others lose angular momentum and sink inward, tightening the central concentration. The galaxy is rearranged by bookkeeping that nature performs automatically. Eventually, the cores merge into a single remnant. The final product is not a spiral pair, because ordered rotation is partly converted into random motion. The remnant becomes more spheroidal, closer to an elliptical or lenticular galaxy. Its light profile smooths out, and its shape becomes less like a disk and more like a glowing three-dimensional ember. This is angular momentum redistribution made visible in structure. Some angular momentum is carried away by tidal tails and outer halo material. Some is absorbed into the remnant's broadened stellar orbits, thickening and rounding the system. The inner regions become dominated by stars on many intersecting paths, which is why ellipticals look smooth rather than patterned. We now separate stars from gas because gas changes the story. Gas clouds collide, shock, and radiate away energy so they do not behave like stars. When the disks interact, gas can lose angular momentum and flow inward. It is the difference between a swarm of bees and a fluid. One passes through, the other compresses. In the gas, collisions are frequent because clouds have large cross-sections and because turbulence stirs them together. When gas streams intersect, they shock, heat, and then cool by emitting radiation. That cooling lets the gas settle into denser structures, which gravity can then collapse further. The merger becomes a machine for concentrating fuel. Compression and shocks raise gas density, and dense gas forms stars efficiently. The result can be a starburst, a temporary spike in star formation rate. The burst is not guaranteed, but it is common in major mergers. The gas is squeezed in tidal arms in central inflows and in colliding clouds that trigger gravitational collapse. Star formation is not magic. It is physics under pressure. When gas becomes dense enough, it cools, fragments, and forms cores that ignite as stars. In a merger, the pressure rises because the gas is stirred and compressed by large-scale torques. The galaxy briefly becomes a factory running at overdrive. The newborn stars appear in clusters and associations, lighting up the dust with ultraviolet radiation. In infrared views, the merger glows where dust absorbs that light and re-radiates it as heat. In optical views, bright blue regions pepper the distorted arms and tidal features. The spectacle is a signature of gas responding to gravity's squeeze. Starbursts are self-limiting because feedback fights collapse. Massive stars produce ultraviolet radiation, stellar winds, and eventually supernovae. That energy heats and stirs the gas, regulating how much of it can turn into stars. The same stars that form in the burst begin dismantling the conditions that made the burst possible. Some gas is driven into outflows that escape the disk region. Some gas is redistributed into the remnant central regions, feeding dense star formation. The balance depends on gas supply, metallicity, and the depth of the combined potential. Metallicity matters because heavier elements help gas cool, and cooling controls how easily gas can collapse. The merger also changes the fate of cold gas reservoirs. Shocks can convert cold gas into warmer phases, and turbulence can keep it from settling. Over time, the remnant can become gas-poor and red, especially if fuel is exhausted. A galaxy becomes red not because it is painted, but because its bright blue massive stars die quickly when new ones stop forming. At the centre of each galaxy is a supermassive black hole. The Milky Way hosts Sagittarius A star, and Andromeda hosts a larger central black hole. Their masses are tiny compared to the galaxies, but their gravity dominates the inner parsec. They are like needles at the centre of enormous whirlpools, small in size yet decisive nearby. The existence of these black holes is now part of modern astronomy's backbone, yet it was once a daring inference. Stellar orbits near the Milky Way's centre revealed an unseen mass confined to a tiny volume. In Andromeda, the central region shows dynamical evidence for an even heavier object. The merger will bring these two central engines into the same gravitational arena. As the galaxies merge, the black holes do not collide immediately. They sink toward the centre through dynamical friction, dragging stars and gas into a denser nucleus. Eventually they form a bound binary, orbiting within the new core. The timescale depends on how efficiently the surrounding matter can carry away energy and angular momentum. The binary hardens by interactions with surrounding stars and gas. Stars passing near the pair can steal energy and be ejected, carving a low-density core. Gas torques can also remove angular momentum if enough gas reaches the centre. In this phase, the nucleus can become a chaotic place, with orbits constantly rearranged by the moving gravitational centre. The final stage is a true merger of horizons, releasing energy as gravitational waves. Space-time rings like a struck drum, and the waveform encodes masses and spins. The signal would be strongest at low frequencies, suited to future space-based detectors. It is the most extreme kind of quiet event, immense energy carried away without light. This black hole choreography is the quiet endpoint of the loudest rearrangement. It is also a reminder that mergers connect galaxy evolution to relativistic physics. The local group event becomes a laboratory in principle, even if no one is there to listen. It is a cosmic story with chapters written in both Newtonian gravity and Einstein's geometry. We bring the scale back to a personal anchor, the Sun. The Sun orbits the Milky Way at about 8 kiloparsecs from the centre. In a merger, its fate is probabilistic because small differences in encounters change long-term outcomes. The Sun is not targeted, but it is not immune to the reshuffling of the gravitational field. What matters is that the Sun is one star among hundreds of billions, and the merger perturbs the statistical distribution of orbits. A close passage of a massive structure, like a dense tidal feature or a passing dwarf, can nudge an orbit over time. The Sun's path could be altered gradually, or it could be kicked more abruptly during a close gravitational encounter. The uncertainty is not ignorance, it is sensitivity. One possibility is outward migration into the remnant's halo. Tidal interactions can pump orbital energy, moving the Sun to a wider, more eccentric path. In that case, the night sky would change dramatically, with denser star fields and new perspectives. The Milky Way's bright band might fade, replaced by a more isotropic glow of stars scattered around. Another possibility is inward migration toward a denser region. That increases the chance of perturbations from passing stars, and increases background radiation from nearby supernovae. It still does not imply direct collision, but it changes the environment. The Sun could find itself in a busier neighbourhood, where gravitational nudges are more frequent and long-term stability is less certain. A third possibility is relative calm, remaining in a moderate radius orbit within the remnant. Many stars will end up in such intermediate regions, because the remnant still has a broad distribution of stable orbits. The Sun's most likely outcome is change without catastrophe. Even then, the familiar geometry of the Milky Way would be gone, replaced by a different kind of galactic home. But solar evolution sets a separate clock that does not wait for galaxies. In roughly 5 billion years, the Sun will leave the main sequence and expand into a red giant. Long before any final galactic merger, Earth's surface conditions will already be threatened by rising solar luminosity. The oceans may evaporate, and the atmosphere may be stripped or transformed, regardless of what Andromeda does. So the merger is not the primary danger to Earth as a habitat. The Sun's own aging is a more immediate limit on life here. The collision is a transformation of skies and orbits, not a guaranteed apocalypse. The danger is not a star hitting us, but time itself. Stellar evolution is the more certain countdown. Now we return to the night sky, because prophecy begins as a visual change. Today Andromeda is a faint smudge, easy to miss under light pollution. It sits beyond the reach of casual attention, a ghostly oval that requires dark adaptation and patience. Yet it is already the largest external galaxy visible to the unaided eye, and that fact hints at what is coming. There is a particular feeling to finding it, because the eye must relax into the dark. The smudge is not sharp, and it does not announce itself like a planet. It is a soft, elongated glow, hovering near familiar constellations like a secret that only appears when you stop trying too hard. That subtlety is part of its power. Over millennia, its apparent size will slowly grow as distance shrinks. At first, the change is subtle, detectable only by careful comparison. Then it becomes undeniable as the disk expands across more of the sky. The galaxy's core brightens, and its dust lanes become clearer to unaided eyes under dark conditions. Imagine standing under a truly dark sky, far from cities, where the Milky Way already casts a faint glow. Andromeda would no longer be a small patch near Cassiopeia. It would become a structured object, with an elongated core and a soft halo that spills outward. The human eye would begin to see it as a place, not a point. As it grows, the mind would struggle to categorize it. It would look like a cloud that does not drift, and like a distant city that does not flicker. The brightest central region would become a steady beacon, while the outer halo would blend into the darkness with a delicate gradient. The sky would gain depth, as if a second landscape were emerging behind the stars. Over tens of thousands of years, Andromeda becomes a dominating arc. Its structure becomes a permanent feature, not a rare object for patient observers. The sky gains a second great band of light, and the familiar constellations lose their isolation. The patterns we name would be overlaid on a new background, and the old stories would have to share space. As the first close pass approaches, the sky becomes dynamic on human historical timescales. The galaxy's shape distorts, and tidal features extend outward. The Milky Way's own disk responds, warping and stretching in return. The two systems begin to look like interacting dancers, their outer arms tracing the forces between them. This is the moment to restate the central question in a new form. What secrets does Andromeda hold about how galaxies collide, and what does that teach us about our own fate? The answer is that collisions are mostly gravity, and gravity rewrites maps without touching most stars. The spectacle is real, but it is a spectacle of trajectories, not of impacts. After the first pass, the sky changes again as the galaxies separate and return. The apparent size may shrink and grow, depending on geometry and distance. The time-lapse is not a single approach, but a sequence of encounters. The sky would feel less like a fixed dome and more like a slow, evolving panorama. In the intervals between passes, tidal tails would hang like faint brushstrokes. Some would be bright with young stars if gas was pulled along and compressed. Others would be dim, visible only as a diffuse glow against the black. The night would carry evidence of forces that act over hundreds of thousands of light years. Eventually, the two disks lose their distinct identities. The remnant's light becomes smoother, less spiral, more like a luminous oval with a bright center. The name Milkomeda, or Milkdromeda, becomes shorthand for a new equilibrium. The word is playful, but the process is profound. two histories become one structure. The remnant is likely elliptical or lenticular, because random motions dominate over thin disk rotation. Some disk-like structure could survive or regrow if enough gas remains and settles. But the dominant morphology will reflect the merger's heating and mixing. The final galaxy would be less about arms and more about a central concentration, wrapped in a broad stellar envelope. This outcome is not special to us, and that is the cosmological context. Mergers are a universal engine of galaxy evolution, especially in the early universe when galaxies were closer and gas-rich. Many giant ellipticals and clusters likely formed through repeated major mergers. When we look at those smooth, massive galaxies, we may be seeing the end state of countless ancient encounters. In deep surveys, we see galaxies in the act of assembly, their shapes irregular and their star formation intense. The early universe was denser, so encounters were more common, and gas fractions were higher. Over time, repeated mergers built larger systems and altered their morphologies. Our future is a late echo of that earlier era. Our local group event is therefore a nearby example of a common process. It connects the faint smudge in our sky to the growth of the largest galaxies we see. The same physics that built Andromeda's past will build our shared future. In that sense, prediction is not speculation. It is the extension of patterns we already observe across the universe. We also note what the merger does not change. The local group remains small compared to the scale where dark energy dominates. Beyond our gravitational island, distant galaxies will continue to accelerate away, becoming unreachable over cosmic time. The cosmic horizon is not a wall you can see, but it is a limit you can calculate. So the merger happens in a universe that is, in the long run, isolating. The local group collapses inward while the rest of the cosmos recedes beyond any future horizon. The irony is that our nearest neighbour becomes our final large companion. The universe grows emptier to us, even as our local sky grows more crowded. This chapter ends on a bridge from prediction to ambition. We can forecast the collision with physics and careful measurement. We can run simulations, vary parameters, and watch plausible futures unfold in accelerated time. Yet the most haunting element is not the certainty of gravity, but the question of presence. If Andromeda is racing toward us through the dark, the race is also ours. Can humans ever get close enough to explore it directly, before the galaxies meet? What would it mean to stand beneath Andromeda's stars, not as a distant glow, but as a surrounding sky? The approach is inevitable, but witnessing it up close is still a choice. Andromeda hangs as a faint smear, yet it is an entire galaxy approaching us through dark. In long exposure images, it becomes a tilted disk, threaded with dust lanes and star clouds, an island universe with 1 trillion suns and a history older than Earth. The central question sharpens here, because curiosity meets a wall of physics that does not negotiate. What secrets does Andromeda hold about galaxy evolution, and will humans ever get close? Distance is the first hard limit, because it is not an abstract number that lives only on paper. Andromeda is about 2.5 million light-years away, which is 2.5 million years at light speed through a vacuum. That number contains a quiet brutality. Light itself, the fastest messenger we know, takes longer than our species has been human. Human civilizations are measured in thousands of years, and recorded science in only centuries, with most of our precision tools younger than a lifetime. Even the age of agriculture is a blink compared to that crossing, and the age of spaceflight is a spark. Put it in human terms, because the mind needs scale to feel truth rather than merely recite it. If the Milky Way were a city, Andromeda would be another continent across an ocean, and the ocean would be black, cold, and without ports. Our fastest probes would still crawl, and the shoreline would never appear within any familiar calendar. The journey is not a trip, it is an era, long enough for coastlines to shift, languages to branch, and the very night sky to subtly rearrange. Even our best instincts about travel mislead us, because we evolved on a planet where distances are small and resources are nearby. In space, there is no air to push against, no refueling stations, and no safe harbour when systems fail. A spacecraft is an island of pressure and heat moving through near-perfect vacuum, and every kilogram has to justify its existence. When we say 2.5 million light-years, we're also saying 2.5 million years of exposure, unless we can change the rules of motion. Conventional rockets fail for a reason that is simple and brutal, and it begins with how momentum is conserved. To accelerate, you must throw mass backward, and that mass is usually propellant expelled at high speed. If you carry more propellant, you must also carry propellant to push that propellant, and then more propellant to push that. The burden compounds until the vehicle becomes mostly fuel, and the payload becomes a thin afterthought at the top of a towering equation. This is the rocket equation, and it is exponential, not linear, which is why intuition breaks. Each extra bit of speed demands a larger fraction of your starting mass as propellant, and the curve steepens quickly. Chemical propulsion is powerful for leaving Earth, because chemical bonds release energy efficiently in a compact engine, yet it saturates quickly for deep space, because chemical energy density is modest compared to what high speeds demand. It is not a matter of will, it is a matter of arithmetic. The deeper reason is exhaust velocity, which sets how effectively a rocket converts propellant into change in velocity. Chemical engines throw exhaust out at a few kilometers per second, which is impressive on Earth but small against interstellar ambitions. Ion engines can reach higher exhaust velocity, and they sip propellant slowly for years, but their thrust is tiny. They are excellent for reshaping orbits, not for sprinting across galaxies. The equation keeps its grip, and it tightens as the destination recedes. Even with ideal staging, chemical rockets cannot approach relativistic speeds, because the mass ratios become absurd. They top out at tens of kilometers per second in practical missions, sometimes a bit more with gravity assist that steal momentum from planets. Voyager 1, one of our fastest emissaries, moves at roughly 17 kilometers per second relative to the Sun. At that pace, Andromeda is not far, it is unreachable, because the travel time becomes a geological epoch. The travel time would exceed the lifespan of species, languages, and continents, and it would outlast the memory of why the probe was launched. It helps to translate that speed into something the body can feel, even if the numbers remain enormous. At 20 kilometers per second, you cross the distance from Earth to the Moon in a few hours, and that feels swift. Yet to cross a single light year at that speed takes roughly 15,000 years, and Andromeda contains 2.5 million of those. The gap between fast and useful widens into a chasm, and the chasm is filled with time. So we acknowledge what we can do now, because exploration already happens without departure. Telescopes are time machines, and they let us study Andromeda without crossing space, because the light we receive left long before our cities existed. We can map its stars, dust, and gas across wavelengths, and each wavelength reveals a different physical process. Infrared shows cooler stars and warm dust. Ultraviolet highlights young hot populations, and radio traces cold hydrogen that fuels future star formation. We can measure its motion precisely, and we can test galaxy formation models with photons alone. This remote exploration has a history, and it is worth remembering how recently we learned what Andromeda even is. A century ago, astronomers argued whether spiral nebulae were nearby clouds or distant island universes. Edwin Hubble's measurements of Cepheid variable stars in Andromeda helped settle the debate, stretching the universe overnight. That shift is part of this chapter's mood. Our reach expands first through measurement, not through engines. The most transformative journeys often happen in data. The exoplanet era sharpens this remote exploration, because it forced astronomy to become obsessively precise. Techniques built for tiny signals, like transit photometry and precision spectroscopy, improve calibration and stability across entire observatories. When you can detect a planet dimming a star by a few parts per 10,000, you learn to tame instrumental drift and stellar noise. Interferometry pushes angular resolution, and wide surveys push depth and statistics, so patterns emerge from faint structure. We learn to separate subtle features from noise, which is exactly Andromeda science. Spectroscopy adds another layer, because it turns light into a chemical and dynamical fingerprint. By measuring Doppler shifts, we can map rotation curves and infer how mass is distributed, including the unseen halo of dark matter. By measuring absorption lines, we can estimate metallicity, how enriched the stars are with elements heavier than helium. Those elements are the ashes of earlier generations, so chemistry becomes a timeline written into starlight. In Andromeda, that timeline helps us reconstruct mergers, bursts of star formation, and long quiet intervals. We can also send probes, but only within our solar system for now, and that limitation still teaches us. Those probes teach us how to survive radiation, cold, and autonomy over decades, where a single software bug can become fatal. They build the engineering culture that interstellar missions would require, including redundancy, fault detection, and graceful degradation. They also remind us how fragile hardware becomes in deep time. As lubricants age, electronics suffer bit flips, and power sources decay. Every year a probe survives is a small rehearsal for a much harder stage. If we cannot send people, we can still send precursors, and the logic begins with mass. Robotic interstellar concepts start with small mass, because small mass is easier to accelerate, easier to shield, and easier to replicate. Breakthrough Starshot proposes gram-scale sails pushed by powerful lasers, trading onboard fuel for a beam that does the work. The idea is to reach a fraction of light speed with no onboard propellant, and to accept that the craft may be disposable. It is a different philosophy of exploration, many tiny arrows instead of one heavy ship. Laser sails shift the problem from propellant to infrastructure, which is still a problem but a different kind. You need a phased laser array with extreme power, stability, and pointing, because a tiny angular error becomes a miss measured in astronomical units. You need a sail that survives acceleration, heating, and beam imperfections, and that keeps its shape under forces that would shred ordinary materials. You need guidance that works while the craft is being pushed like a leaf in a hurricane, with photons as the wind. Even the sail's reflectivity becomes life or death, because absorbed light turns into heat. There is also a timing problem that hides inside the elegance of the concept. The laser must stay locked on target while Earth rotates, while the atmosphere distorts, and while the craft races away. That implies adaptive optics, space-based arrays, or both, and it implies a level of coordination that resembles a global observatory. The beam itself becomes a piece of infrastructure that must be maintained for years and maintained without interruption. A sail mission is therefore not only physics, it is commitment. Even if Starshot works for nearby stars, Andromeda is a different category, and categories matter in astronomy. A probe at 20% of light speed still needs over 12 million years to arrive, because 2.5 million light-years divided by 0.2 c is still enormous. That is longer than the existence of Homo sapiens, and longer than the time since our ancestors first used fire. It is longer than the time since the last common ancestor of humans and chimpanzees, and it dwarfs the entire written record. The numbers do not merely disappoint, they redefine what mission means. Scaling also collides with collision hazards, and the danger grows with speed in a way that feels unfair. Interstellar space is thin but not empty, and dust grains become bullets at relativistic velocity. A speck of dust carries enormous kinetic energy when you hit it near light speed, because energy scales with the square of velocity and then climbs even faster as relativity takes over. What would be a harmless mote in a laboratory becomes a microscopic meteor, delivering energy in a violent, localized flash. The craft is sandblasted by an invisible storm. It is worth picturing the visuals, because the threat is otherwise too abstract to fear. Imagine a dark hull moving through a field of glittering grains, except the grains are mostly unseen, and the impacts happen as brief bursts of plasma. Each strike excavates a tiny crater, ejecting molten material and secondary fragments that can ricochet into sensitive systems. Over years, the surface erodes like rock in a desert wind, but the wind is made of atoms. At high enough speed, the boundary between travel and impact begins to blur. Shielding for that storm is not optional, and it is not easy, because every solution fights the rocket equation. A thick physical shield adds mass, which reduces achievable speed and increases energy requirements. A thin shield fails, because impacts vaporize material and create secondary debris that spreads damage. Some designs imagine a sacrificial Whipple shield, spaced layers that disperse impact energy before it reaches the main hull, yet at relativistic speeds, even clever layering can be overwhelmed, and the medium itself becomes the enemy. Relativity offers a seductive loophole, and we must state it carefully to avoid turning physics into wish. If a craft could travel near light speed, time dilation would reduce the crew's experienced travel time, because moving clocks run slow relative to stationary ones. The outside universe would still wait millions of years, but the travellers might feel far less, perhaps even a few decades. Physics permits this, and it has been tested with particles and precision clocks, but it does not gift it freely. The loophole comes with a price tag written in energy and hazard. Time dilation is not science fiction magic. It is measured reality, and it appears in everyday technology. GPS satellites must correct for both special and general relativity, because their clocks tick differently than clocks on Earth. In particle accelerators, unstable particles live longer when moving near light speed, because their internal clocks run slow. The effect grows as velocity approaches light speed, and the curve is steep. At 99% of light speed, the factor becomes dramatic, and a crew could cross vast distances within a human lifetime of onboard time. But the energy requirement becomes the next wall, and it rises steeply as you approach the speed limit. Kinetic energy scales with the relativistic gamma factor, not just with v squared, so each additional fraction of c costs more than the last. Pushing a large ship to near light speed demands energy comparable to planetary outputs over long periods. You must store it, generate it, or beam it across space, and each option carries its own engineering nightmare. The ship is no longer a vehicle, it is an energy project. There is also a symmetry that is easy to forget, and it makes the problem harsher. If you accelerate to near light speed, you must also decelerate when you arrive, unless you accept a flyby that lasts minutes. Deceleration requires the same magnitude of momentum change, which means the same scale of energy and propellant, or an external braking method like a beam or a magnetic sail. Without braking, arrival is just passing through at lethal speed, a brief glimpse before darkness returns. The destination becomes a blur. Energy is not the only cost at high speed, because shielding becomes existential, and the environment changes in the ship's frame. Cosmic rays are already dangerous at rest, and they become worse when you plough through the interstellar medium at relativistic velocity. In the ship's frame, incoming particles are blue-shifted into higher energies, and even ordinary hydrogen atoms arrive like radiation. Space turns into a furnace of particle impacts, and the hull becomes the first line of biology. The faster you go, the more hostile empty becomes. The radiation environment has two main sources, and both are relentless across deep time. Galactic cosmic rays are high-energy particles accelerated by supernova remnants, pulsars, and other violent magnetic structures. The interstellar medium adds atoms and dust that strike the hull at extreme energies, producing showers of secondary particles. Together they create chronic dose and acute impact risk, and the risks compound over years. Radiation is not a single event, it is a slow pressure on cells and electronics. A human mission must solve radiation with mass, fields, or both, and each approach has limits. Massive shielding can attenuate particles, especially if it is hydrogen-rich material that reduces secondary neutron production. Yet shielding increases launch mass and energy needs, and thick shields can still generate harmful secondaries when struck by high-energy ions. Electromagnetic deflection could bend charged particles, but it demands power and careful field geometry, and it does nothing for neutral particles. Neutrals and high-energy secondaries still penetrate, and biology remains vulnerable. The health stakes are not vague, because we understand radiation damage at the molecular level. High-energy particles break DNA strands, create reactive radicals, and increase cancer risk, while also harming the nervous system and cardiovascular tissue. Acute doses can cause radiation sickness, but chronic lower doses are the more likely threat on long voyages. Even if a crew survives, their reproductive health and long-term cognitive function become part of mission planning. The ship must be a medical system as much as a transport system. Life support is another wall, because humans are ecosystems, not payloads, and ecosystems have preferences. Air, water, food, and waste must cycle with near-perfect closure for centuries or longer, and closure is hard because nothing is perfectly sealed. Microbial dynamics can destabilize, and small leaks become catastrophic over time because resupply is impossible. Trace contaminants accumulate, and tiny imbalances in carbon dioxide or humidity can cascade into illness. The ship becomes a biosphere under stress, and stress finds the weak link. Generation ships confront this directly, and they shift the question from propulsion to civilization, which may be an even harder discipline. A multi-century or multi-millennia voyage requires stable governance, education, and purpose, because children must inherit a mission they did not choose. It requires genetic diversity to avoid inbreeding and drift, which implies a minimum population and careful reproductive planning. It requires social continuity without coercion, because coercion corrodes legitimacy over time. The ship is not merely carrying people, it is carrying a culture. Ecological stability is harder than it sounds, because closed systems amplify feedback and reduce buffers. A small imbalance in nutrients can cascade through crops and microbes, shifting yields and altering diets in ways that affect health. Pathogens evolve, and monocultures invite collapse, so diversity becomes a form of insurance. Even pollination, soil structure, and plant microbe symbiosis become engineering concerns. The limiting technology becomes biology, not engines, because biology is non-linear and stubborn. There is also the psychological physics of isolation, which is still physics in the broad sense of constraints and forces. A crew cannot be rescued and cannot return, and cannot receive real-time guidance because the outside world is separated by time as well as distance. Culture must survive boredom, conflict, and meaning loss across generations, and it must do so in a habitat where privacy is scarce. The mission must be a society that can endure itself, and endurance is not guaranteed by good intentions. What happens when the story that launched the ship stops feeling true? Suspended animation is often proposed as a way around that burden because it seems to compress time. If you could pause metabolism, you reduce food, water, and social complexity, and you reduce the number of lives lived inside a corridor. Yet cryopreservation at human scale remains unsolved, and the obstacles are physical rather than poetic. Ice crystals rupture membranes, concentration gradients poison cells, and rewarming large tissues evenly is extraordinarily difficult. Revival fidelity is not a minor detail, because failure is death. Even if tissues can be preserved, brains are the hardest case, because brains encode identity and delicate structure. Memory and personality depend on synapses, dendritic spines, and biochemical states that must survive freezing and thawing without rearrangement. Vitrification reduces ice by turning water into a glass-like solid, but it introduces toxicity and thermal stress. Cracks can form during cooling, and subtle damage might not be visible until function fails. The gap between preserving cells and preserving persons remains wide, and it is not yet narrowing fast. Digital minds are a different speculative path, and it is grounded as a thought experiment rather than a promise. If cognition could be emulated, the payload becomes computation and power, and the crew becomes software that can be copied and backed up. You trade life support mass for hardware redundancy and radiation-hardened systems, and you can potentially tolerate long durations without boredom. You also trade ethics for engineering, and the ethics are not optional, because personhood is not a technical parameter. If a mind is copied, which copy is the traveller? Brain emulation is not a near-term plan, and we should say why with clarity. We do not yet understand the full neural code, and we cannot scan a living brain at the required resolution without destroying it. Even if we could scan perfectly, we do not know what level of detail preserves subjective continuity, or whether continuity is even definable in that way. The concept reduces mass, but increases uncertainty, and uncertainty is a cost. It is a reminder that some barriers are epistemic, not mechanical, so propulsion returns as the central bottleneck, because everything else depends on speed, and speed depends on energy. Fusion rockets are the first serious step beyond chemical energy density, because fusion taps nuclear binding energy rather than chemical bonds. Fusion offers far higher exhaust velocity, which helps the rocket equation, and it could in principle sustain high delta V without absurd mass ratios. Yet controlled fusion in a compact, reliable engine is still unproven, and even terrestrial fusion remains an unfinished chapter. The difference between a laboratory plasma and a flight engine is the difference between a spark and a furnace. Even if fusion works, fuel handling and reaction products matter, and the details are unforgiving. You need confinement, ignition, and a way to direct exhaust, which implies magnetic nozzles, radiation management, and robust materials. Many fusion reactions produce neutrons, and neutrons are hard to shield because they are uncharged and deeply penetrating. Neutron bombardment embrittles materials and activates them, turning structure into a radiation source. Engineering must operate for decades without maintenance, which is a different kind of difficulty than a short mission. Antimatter is the most energy-dense known fuel, and it is also the most impractical, which is why it haunts speculation. Producing antimatter costs enormous energy, because we must create it particle by particle in accelerators. Storing it requires perfect isolation, because contact with normal matter releases energy violently. A containment failure is not a leak, it is an explosion, and even small amounts are dangerous. Antimatter catalysis might reduce required amounts by triggering fusion, but it remains far future and far expensive, beamed power offers another route, and it aligns with laser sail thinking because it externalizes the energy source. Instead of carrying fuel, you push or power the craft from home, which reduces onboard mass and avoids some storage problems. Yet it demands a transmitter that stays aligned for years, and alignment is harder than it sounds across astronomical distances. It also demands a political commitment to keep the beam on, because the mission becomes a long-term infrastructure service. The engine is no longer inside the ship, it is behind it. Over interstellar distances, beam divergence becomes a tyrant, because diffraction spreads any finite beam. The receiver gets less power with distance, and the fall-off is merciless unless apertures become enormous. To keep intensity, you need vast optics and precise phasing, and you must control thermal distortion as power flows. The infrastructure becomes a megastructure, and the mission becomes a civilization project rather than a single launch. The physics is clean, but the engineering is monumental. The Bussard ramjet is often cited as a clever solution, and it has a real physical constraint that makes it a useful lesson. It proposes scooping interstellar hydrogen and fusing it for thrust, turning the medium into fuel. But interstellar density is extremely low, often just a few atoms per cubic centimetre, and the scoop must be enormous to collect meaningful mass. Drag from collecting mass can exceed thrust at high speed, turning the engine into a brake. The more you try to harvest, the more the universe pushes back. In realistic analyses, the ramjet struggles because the medium is too thin and because the fusion itself is not easy. Fusion of collected protons is hard because proton-proton fusion is slow, which is why stars need immense pressure and long time. Alternative cycles require heavier fuels that are even rarer in interstellar space, undermining the scoop-as-you-go promise. The concept teaches a lesson about space, which is that emptiness defeats easy harvesting. It is a beautiful idea that collides with sparse reality. Hypothetical drives appear at the edge of physics, and we keep them labelled to avoid confusing math with engineering. Warp metrics and wormholes exist as solutions in general relativity, but they require exotic energy conditions that violate familiar constraints. Negative energy density is not something we can engineer at scale, and even its existence is subtle and limited in known quantum effects. The math permits, but nature may refuse, and history is full of permitted equations that never become machines. Speculation can inspire, but it cannot substitute for materials. Navigation becomes its own crisis when the trip lasts millennia or more. Because motion is never perfectly straight in a dynamic universe. You must maintain a course across gravitational tides, passing stars, and changing reference frames, while the galaxy itself rotates and evolves. Tiny errors accumulate into vast misses over millions of years, so a small bias in thrust becomes a catastrophic drift. The craft must constantly measure, decide, and correct, using stars as beacons that slowly change position. In deep time, even the map is moving. The instruments for that navigation must be both precise and durable, which is a rare combination. Star trackers must recognize constellations that will subtly distort over long durations, and inertial systems must resist drift. Pulsar timing has been proposed as a kind of galactic GPS, because pulsars are stable cosmic clocks. Yet stability is not perfection, and the craft must interpret signals through noise and distance. Navigation becomes a conversation with the universe's own metronomes. Communication is bounded by the same light speed that defines the distance, and the consequence is emotionally strange. Even at light speed, messages take 2.5 million years each way, so there is no conversation, only archaeology of intent. A craft could send a signal, and the reply would arrive after entire species might rise and fall. Earth will be a different world by the time any signal returns, with different coastlines, different politics, and perhaps different biology. The mission must be autonomous, because guidance from home is a myth. That autonomy implies AI governance, and it raises both capability and trust, because the system must act as caretaker and judge. The system must handle failures, resource allocation, and mission drift without human oversight, and it must do so under uncertainty. It must resist corruption from radiation-induced errors, and it must resist emergent behavior that diverges from mission goals. Redundancy helps, but redundancy can also create conflicts that must be resolved. The ship becomes a self-ruling machine in deep time, and the ethics of that machine matter. We also return to the earlier theme of measurement limits, because they echo here with higher stakes. In Chapter 5, we measured micro-arc-second motions to predict a merger, and that precision felt like triumph. For a probe, micro-arc-second navigation becomes survival, not just science, because the target is small against the void. Precision is not luxury, it is the difference between arrival and endless drift. Between a close pass and a miss by light years. The same mathematics that tracks galaxies would have to steer a craft. If physical travel is daunting, we ask what it means to get close in another way because closeness can be informational. Gravitational lensing offers a form of virtual proximity that uses mass as an optical element. A telescope placed at the sun's gravitational focus could use the sun as a lens, bending light into a thin, powerful ring. It could, in principle, resolve distant targets far beyond conventional apertures, turning our star into part of the instrument. The idea feels like science fiction, yet it is a direct consequence of general relativity. The solar gravitational lens begins around 550 astronomical units, which is far but not unimaginable, and it sits like a threshold. Reaching it still takes decades with current propulsion, and station keeping is hard because the focus is not a single point but a long line. The spacecraft must move along that line, sampling the Einstein ring and reconstructing an image through computation. Yet it is within the solar system, which keeps logistics and energy closer to human timescales. It's a bridge between here and there, built from geometry rather than thrust. Multi-messenger astronomy is another kind of closeness, because it adds new channels to our senses. Neutrinos pass through dust and gas with little absorption, carrying information from dense regions where photons struggle to escape. Gravitational waves carry information from massive accelerations like black hole mergers, and they do so without being scattered by matter. Together they let us probe Andromeda without photons alone, adding depth to the story. Each messenger is a different kind of testimony, and the universe rarely lies in all channels at once. Future interferometers extend this idea by synthesizing enormous apertures, and the principle is already proven. Arrays in space could achieve micro-arc-second resolution, mapping stellar motions and compact objects in Andromeda with exquisite detail. With enough baseline, we can watch dynamics, not just snapshots, and we can see how star clusters orbit and dissolve. We can test merger history and dark matter structure with unprecedented precision, because motion reveals mass. The galaxy becomes a laboratory, and we become patient observers. There is a visual poetry to this kind of exploration, because it makes the distant feel textured. A radio map can reveal vast hydrogen streams arcing around Andromeda, like faint rivers feeding a rotating disk. An infrared mosaic can show the glow of older stars smooth and golden, while ultraviolet spots flare when new stars ignite. Overlaid velocity fields can turn the galaxy into a living weather map, with rotation, turbulence, and inflow marked in colour. We do not touch Andromeda, yet we learn its habits. This is where the mystery deepens rather than closes, because knowledge expands faster than reach. Physics does not forbid intergalactic travel, but it prices it in energy, time, and risk, and the price is not symbolic. Engineering does not yet know how to pay that price, and biology does not yet know how to endure it. Our species is caught between what equations allow and what materials can survive, and the gap is measured in orders of magnitude. The gulf is not only between galaxies, but between capability and desire, so we frame exploration as a continuum, not a binary, because the universe offers many gradients of closeness. Today we explore with light, spectra, and simulations, and we already learn Andromeda's hidden history in streams of stars and faint halos. Tomorrow we may explore with lenses, interferometers, and robotic precursors that extend our senses beyond the limits of single mirrors. Far later, if we master energy and biology, we might send minds or bodies across the gulf, accepting that the mission will outlast its origin. The timeline is humbling, yet it is also a kind of invitation. We tie back to the biography and the approach, because this chapter is the climax of ambition rather than a defeat. Andromeda's past is written in mergers, and its future includes our own collision, a slow dance that will reshape both galaxies. The question is whether we can meet it as observers, or only as descendants of photons reading the story at a distance. The smudge remains distant, yet it keeps pulling on our imagination, because it is both neighbour and prophecy. When we look at it, we are looking at a future sky. If physical travel is daunting, Andromeda still offers something profound now, and it does not require a launch window. By studying it, we learn how galaxies form, evolve, and collide, and we learn what our own sky will become over billions of years. The universe is alive with slow-motion change, and it is knowable across an ocean of dark if we are willing to be precise and patient. The final chapter asks what we do with that knowledge, while time still belongs to us. And in that question, the distance becomes more than a barrier, it becomes a mirror. Andromeda answers our question by showing galaxies are ecosystems, built in darkness and revised by time. In wide-field images it looks serene, yet its outskirts glow with faint starlight, fossils of earlier lives. Its disk grew calmly from cooling gas inside a dark matter halo, while its halo debris records repeated hierarchical accretion. In plain terms, the smooth spiral is only the surface layer of a long, uneven assembly. Streams, shells, and a heavy bulge imply mergers that heated the disk, then allowed rebuilding. Those arcs are not artistic flourishes. They are phase-wrapped tidal debris, stars stretched along orbits by gravity's differential pull. Some streams trace the paths of swallowed dwarfs, and some shells mark where stars pile up near orbital turning points. The bulge itself hints at violent relaxation. When many stellar orbits were scrambled into a thicker, hotter component, dark matter sets the stage, shaping rotation curves, satellite orbits, and the invisible boundary of what stays bound. The flatness of those curves is the clue that first forced astronomers to accept missing mass, long before we could map it indirectly. In Andromeda, the halo's mass controls how tightly streams remain coherent and how quickly they dissolve into a smooth glow. We watch the luminous traces, then infer the dark architecture that holds them. The local group becomes our laboratory, close enough to resolve stars and test feedback. With individual stars counted and dated, we can reconstruct when bursts of star formation ignited and when supernovae drove gas outward. That feedback matters because it can puff up inner dark matter, alter dwarf galaxies, and change what substructure should look like. Here we confront missing satellites, too big to fail tensions, and whether dark matter is cold, warm, or something stranger. Andromeda also keeps its secrets, and the unknowns sharpen the mystery. We still debate its major merger history, because the disk is thin in places, yet the halo is richly disturbed. We argue over M33's past passages, which could have tugged at Andromeda's disk and stirred its outer gas. And we still ask why satellites align in thin planes. Are we seeing chance, or a dynamical memory we have not decoded? Even the collision clock remains uncertain, because tangential motion and halo mass still carry error bars. Proper motions are tiny at this distance, measured as microshifts against background galaxies, and small systematics can tilt the forecast. The first close pass is likely in 4 to 5 billion years, yet the exact choreography is not settled. Will the encounter be a clean swing by, or a quicker plunge into a shared, distorted halo? Beyond this bound pocket, the universe accelerates, and expansion steadily wins on large scales. Dark energy stretches the cosmic fabric, so the most distant galaxies drift away faster than light can return their signals. Over deep time, distant galaxies slip beyond the observable horizon, leaving only local gravity's island. The sky's deep background dims, not because stars stop shining, but because their light can no longer reach us. So the future is paradoxical, with our sky growing crowded as the cosmos grows empty. The local group will merge inward while the rest of the universe fades from reach. In simulations, tidal tails flare like pale ribbons, then fall back, and the remnant settles into a single massive galaxy. The night becomes quieter in one sense, yet more intimate. One dominant system, one shared fate. If we cannot travel to Andromeda soon, we can still explore it with instruments that extend mind into measurement. Next-generation space telescopes, wide-field surveys, and interferometers will resolve stars, map gas flows, and find exoplanets in nearby galaxies. Spectra will turn starlight into chemistry, revealing where elements formed and how quickly enrichment spread through the disk. Proper motion baselines will lengthen, and the halo's shape will become less guesswork and more geometry. Every calibration improvement tightens the distance ladder, pressures the H0 tension, and turns Andromeda into a benchmark. Standard candles like Cepheids and the tip of the red giant branch become more reliable when crowding and dust are modelled precisely. Getting close becomes an act of understanding, where precision is a step across the void. Each reduced uncertainty is a quieter kind of voyage, made with photons and patience. we return to the faint naked eye smudge, now reinterpreted as a vast system with a violent past. Under dark skies it hangs like breath on glass, but in our minds it expands into a disk of hundreds of billions of stars. It is also a message from deep time, approaching through dark matter we cannot yet name. The closer it comes, the more it forces a question. What is the unseen mass that guides every visible curve? Andromeda's secrets are the universe's secrets, how structure forms from darkness, how time reshapes light, and how gravity writes galactic destinies. Humans may not cross the gulf soon, but we are already reaching it with our minds and instruments. In that reach, the galaxy stops being a distant object and becomes a mirror, reflecting the long future of our own sky. We began with a ghostly smudge and ended with a living system, a spiral giant whose light is a time capsule. Along the way, Cepheids turned Andromeda from nebula into an island universe, and the distance ladder became both our bridge and our vulnerability. We mapped its disk and ring, read its dust and newborn stars in many wavelengths, and then followed the faint halo streams and shells that betray ancient meals. We watched dark matter reveal itself by what it holds together, and we saw how missing baryons may linger in a hot, unseen circumgalactic sea. We measured a steady blue shift, chased micro-arc seconds of proper motion, and learned that the coming encounter is less a crash of stars than a slow rearrangement of gravity. And when we asked whether we could ever go, physics answered with uncomfortable honesty, yet offered new kinds of closeness through lenses, interferometers, and patient machines. And still, the story refuses to be simple, because every image of Andromeda is already 2.5 million years old, and every conclusion is stitched from delayed light. The streams might record one great upheaval, or 1,000 smaller scars. The satellite planes might be real architecture or a trick of incomplete maps. An M33 may be a past sculptor or merely a distant companion. Even the Milky Way's future choreography remains a probability cloud, shaped by halo mass and tangential speed, by systematics we have not fully tamed. In that uncertainty, Andromeda becomes more than a neighbour. It becomes a test case for how we do cosmology at all. Because Andromeda sits close enough to resolve into individual stars, yet far enough to feel like a separate universe, it is where our tools are forced to confess their limits. Dust reddening, metallicity shifts, crowding in bright fields, and subtle calibration biases can tilt Cepheids, TRGB, and secondary indicators, and those tiny tilts can echo outward into masses, ages, and the expansion rate itself. The H0 tension, that quiet disagreement between the nearby universe and the early one, is not solved by staring at Andromeda, but it is sharpened by it, and sometimes sharpening is how progress begins. Each refinement, Gaia's parallax anchors, Hubble's stable photometry, new standard candles, better extinction maps, turns Andromeda into a more precise ruler and a more demanding judge. What we learned then is not merely what Andromeda is, but what a galaxy is allowed to be. A disk can look serene while its halo remembers violence. A bulge can form fast and old, while the outskirts keep the slow-motion debris of swallowed worlds. Dark matter can be invisible and still leave fingerprints in rotation curves, stream gaps, and satellite orbits, and its true nature, cold, warm, or stranger, may be written in the local group's smallest structures. The universe, in Andromeda's example, is not a museum of fixed objects. It is a workshop where gravity builds, unbuilds, and builds again. And we learned that the future is already embedded in the present, if you know where to look. Andromeda's approach is measured in spectral lines, but its fate depends on sideways motion that is almost too small to see, and on halos that overlap like invisible weather. Whether the first pass is a clean swing by or a quicker plunge, tides will draw out long luminous tails, gas will shock and ignite, and the two disks will lose their ordered spin into a single rounder remnant. Somewhere inside that remnant, two supermassive black holes will begin the last uncertain dance, and whether the final parsec yields easily or stubbornly will decide when the sky itself rings with gravitational waves. The collision, when it comes, will not be a sudden apocalypse but a slow rewriting of the constellations, an ending that is also a kind of beginning. Andromeda also forced us to admit what explore really means across an intergalactic ocean. A ship that feels fast in human terms still crawls on cosmic scales, and communication delays turn any mission into a message to a future civilization. Yet exploration is not only footsteps on alien soil, it is also the patient accumulation of truth from faint photons and the courage to build instruments that outlast their makers. A sail pushed by light, a probe guided by pulsars, a telescope using the sun as a lens. These are not fantasies so much as long bets placed on curiosity. So what secrets does Andromeda hold about how galaxies form, evolve, and collide? And will humans ever get close enough to explore it before the impact rewrites our sky? The secrets are not stored in one hidden chamber, they are distributed across its structure, its chemistry, its debris fields, and its motion, and they tell a single, unsettling lesson. Galaxies are not stable islands, they are histories in motion. As for closeness, Andromeda may remain physically unreachable for bodies like ours, but it's already within reach of our measurements and our models and the expanding definition of what it means to arrive. In the end, Andromeda is both a destination and a mirror, and the mirror matters more because it reflects the Milky Way's own biography back at us. When you look at that faint smudge, you're watching a galaxy that has survived mergers, grown rings, swallowed companions, and carried its dark halo like an unseen skeleton. Exactly the kind of life our own galaxy has lived, and will live again. The night sky feels permanent only because our lives are brief, and Andromeda is the proof, written in pale light, that permanence is an illusion. And perhaps that is the most human secret it offers, that the universe is mysterious and violent, yet increasingly knowable if we accept deep time as our true scale. The photons crossing the void do not promise comfort. They promise connection, and they remind us that understanding is a form of travel, one that can begin from a backyard shadow, under a sky dark enough to reveal the smudge. If you want to keep going, look up on a clear night, find the faint blur in Andromeda, and remember that every careful measurement you support brings that ancient light a little closer to meaning. So what secrets does Andromeda hold about how galaxies form, evolve, and collide? And will humans ever get close enough to explore it before the impact rewrites our sky? The secrets are not stored in one hidden chamber. They are distributed across its structure, its chemistry, its debris fields, and its motion, and they tell a single, unsettling lesson. Galaxies are not stable islands, they are histories in motion. As for closeness, Andromeda may remain physically unreachable for bodies like ours, but it is already within reach of our measurements and our models and the expanding definition of what it means to arrive. When you look at that faint smudge, you're watching a galaxy that has survived mergers, grown rings, swallowed companions, and carried its dark halo like an unseen skeleton. Exactly the kind of life our own galaxy has lived and will live again. The night sky feels permanent only because our lives are brief, and Andromeda is the proof, written in pale light, that permanence is an illusion. If you want to keep going, look up on a clear night, find the faint blur in Andromeda, and remember that every careful measurement you support brings that ancient light a little closer to meaning.